Let's travel back 500 million years into the past. A dead, silent world unfolds before us. Not a single green sprout will be seen on the rocky shores of ancient Earth. Life had not yet taken its boldest step, emerging onto dry land. How was it that fragile organisms entirely dependent on the water were able to give birth to gigantic forests that would eventually transform our entire planet? This narrative will unfold before you the grand saga of the great conquest of the continents. Which creature, in your opinion, was the true pioneer of this expedition? Now, let's begin our journey. Look at these coastal waters, washing over endless deserted shores. Here, in the shallows, rocky ridges, sandbars, and mudflats are scattered. Every day, these surfaces are subjected to harsh tests, sharp temperature changes, and parching sunlight. The atmosphere itself was completely different back then. The air here is a thick cocktail of carbon dioxide, virtually devoid of complex organic compounds. Only after eons of time will it be saturated with life-giving oxygen. And now, on these lifeless shores, we see the tentative signs of nascent life. Microbial mats begin their slow but steady growth, spreading across the damp sediments and forming dark, living carpets. Cyanobacteria and other primitive photosynthetic organisms weave into a fine film that, like a living net, captures the smallest particles of silt and sand, holding them in place. Sugars produced in sun-drenched leaves can now travel throughout the organism, down to feed hungry roots in the dark soil, upwards towards the rapidly growing shoots, and to the sides towards the forming seeds and spores. This astonishing ability to transport nutrients in any direction transforms the plant into a single, fully integrated organism. It can now coordinate its growth, directing resources to different parts of its body as needed. The structure of the phloem itself is very different from the dead, woody tubes of xylem. Phloem cells remain alive, their walls thin and riddled with pores, allowing sweet sap to flow freely from one cell to another like a living conveyor belt. Later, they will be joined by satellite cells that will help service and maintain this complex system. The evolution of vascular plants took a giant leap forward. The sugar delivery system became the heart that nourished the entire organism. In the very first explorers of land, it was still primitive, but already incredibly effective. Simple, elongated cells running parallel to the xylem ensured an uninterrupted supply. Together, xylem and phloem formed vascular bundles that penetrated the stems and roots, weaving all parts of the plant into a single whole. The emergence of this dual system marked a true flowering of plant life. Plants could now reach gigantic sizes and develop far more complex forms than their ancestors. But that's another story entirely. Let's travel back millions of years to an era when life was just beginning its great march onto land. It is here, at the dawn of time, that a quiet but momentous revolution unfolds. Plants. These pioneers of the New World make a fundamental breakthrough. They begin to grow roots, powerful, tenacious tendrils that dig into the rocky soil. This is not just a change in form. It is a radical transformation of their entire survival strategy. Imagine, plants now have an anchor. Roots anchor them firmly in the ground, resisting wind and rain and all the vagaries of the elements. But more importantly, they are their conduit to resources. By penetrating deep, they access life-giving moisture and minerals hidden beneath the surface. This gives them an unprecedented boost to growth. Essentially, roots become the inseparable bond that binds plants to the planet, providing them with both physical stability and the ecological foundation for future prosperity. With this invention, the great conquest of land gains momentum, paving the way for the dense, lush landscapes we will see in eras to come. As the plant world takes deeper root in the soil, establishing its position, the next key adaptation appears. This is an internal change that will change the rules of the game. To truly conquer continents and expand beyond the damp, swampy lowlands, plants needed an efficient way to transport water and nutrients throughout their bodies. The old method, diffusion, where substances slowly trickle from cell to cell, worked only over microscopic distances and was completely useless for larger creatures. And nature finds a brilliant solution: vascular tissue. Its first component, a true engineering marvel of evolution, is xylem. This specialized tissue, whose sole function is to pump water upward, from the very tips of the roots to the outermost leaves. Imagine an amazing system of microscopic pipelines. Xylem consists of elongated hollow cells connected end to end, but their walls are more than just a thin membrane. They are reinforced with lignin, an incredibly strong organic polymer which gives them rigidity and protects them from deterioration. Through these internal channels, like arteries, water and dissolved minerals rush from the soil upward to where the leaves catch sunlight for photosynthesis. The emergence of xylem forever changed the face and scale of plant life. Thanks to this perfect water supply system, plants no longer had to spread out like a thin carpet along the ground. They could now boldly stretch upward, raising their green leaf panels toward the sun, outpacing their primitive competitors in this race. This battle for light, for a place in the sun, unfolds vertically. Access to sunlight becomes the main currency in new ecosystems, and those at the top gain everything. But how can a tiny stem defy gravity and the force of the wind? And here, xylem reveals its second, no less important talent. Lignin-reinforced cells are more than just a water supply. They are an internal skeleton, a supporting framework. Xylem performs a dual function. It is both a transport highway and a reinforcement that gives the plant strength. It is this combination that lays the foundation for the emergence of truly vertical stems and, in the distant future, the mighty trunks of giant trees. The fossil record bears witness to these first steps. In Silurian deposits, paleontologists have found traces of the earliest xylem. These are among the first vascular plants, such as Cooksonia. These humble pioneers were small branching stems with a central vein of xylem. Although they were no more than a few centimeters tall, their structure itself represented a giant leap forward. Analysis of fossilized cell walls confirmed the presence of lignin, a material that already served as natural concrete. But lignin has another remarkable property, important not only for the plant itself, but for the entire planet. It is incredibly resistant to decay. This stubborn polymer means that after a plant dies, its tissues decompose very slowly. They remain in the soil for a long time, becoming part of geological sediments and preserving organic carbon for millions of years. How does this ingenious system work? Xylem physiology is based on the simple yet elegant principle of cohesion and tension. Imagine, when water evaporates, From the surface of leaves through microscopic pores, it creates a suction effect that pulls the entire water column along with it, all the way from the roots. This continuous column of water is held together by the cohesive forces between the water molecules themselves. It's a kind of natural pump, operating without a single muscle. The system is simple, yet incredibly effective. In the first vascular plants, it lifted water only a few centimeters, but the principle was there. It was this principle that would eventually enable the gigantic forests of the Devonian period and subsequent eras to deliver tons of water to dizzying heights. The ecological consequences of xylem's emergence were immediate. Plants with vascular tissue become true dominant plants. They grow faster and more reliably than their primitive counterparts. They more effectively colonize new territories, ruthlessly winning the competition for light and space. Their stems rise above the carpets of mosses and lichens, casting shade and altering the microclimate at the ground surface. Under their cover, the soil remains moist longer, creating more favorable conditions for both the plants themselves and other organisms. Thus, with the emergence of xylem, plants begin to transform not only themselves, but also the entire environment, becoming the first planetary engineers. Lignin, the durable material found in xylem walls, is beginning to influence global processes. Because it decomposes so poorly, vast masses of plant remains do not release their carbon back into the atmosphere. The carbon is locked up in soils and sediments for long periods. This leads to a gradual but steady decline in atmospheric carbon dioxide levels. In the Silurian and early Devonian periods, this effect was still barely noticeable. But as vascular plants become larger and more numerous, it will become one of the main factors altering the planet's climate. Even at this early stage, the chemical stability of lignin begins to reshape the global carbon cycle. The evolution of xylem opens up entirely new horizons for plants to experiment with form. With a reliable support and transport system, they can branch to maximize the area they capture sunlight. Fossils from those times reveal dichotomous branching, when the stem simply splits into two identical parts. This arrangement not only increases photosynthetic capacity, but also provides additional structural stability. Each new branch receives its own supply line, allowing the plant to utilize resources most efficiently. The combination of vertical growth and branching begins to create an entirely new form of plant life, far more complex and voluminous than the primitive flat mats of past eras. As these xylem-bearing plants grow, their influence on the soil only intensifies. Their root systems become more powerful, and their vascular transport becomes more extensive. The roots penetrate deeper, chemically altering the rock and binding the loose soil together. A powerful feedback system emerges. Stronger roots support taller stems, and taller stems produce more organic matter, which, after death, enriches the soil. With each generation, this cycle accelerates the processes of soil formation. Landscapes that were recently bare rock or a thin layer of sediment now begin to be covered with a continuous green canopy. The appearance of xylem even indirectly influences reproduction. By raising their sporangia, the organs that produce spores, higher above the ground, plants gain a huge advantage. Up there, the wind is stronger, picking up the microscopic spores and carrying them over vast distances. This allows them to effectively colonize new, previously uninhabited areas of land. Thus, xylem doesn't just facilitate the growth of individual plants, it becomes the engine of expansion for entire populations, facilitating their rapid spread across all the continents of the ancient world. Take a look at this landscape. It's changing before your eyes. Where once the land was covered only in flat, monotonous mats, the first vertical structures are appearing. These modest shoots, just a few centimeters tall, create a new, astonishing dimension. They may seem insignificant, but their silhouettes pierce the low horizon of ancient coastlines. Branching stems form dense thickets in the damp lowlands, breaking the monotony of the flat terrain. To any observer, the earth begins to look less barren, more alive and structured. The emergence of xylem also creates the conditions for new ecological interactions with the animal world. Early arthropods, timidly exploring land, encounter these vertical structures. They become shelters and entire microhabitat worlds. Insects and other small invertebrates find shade under the stems, escape desiccation in the moist litter, and feed on rotting organic matter. The complexity of terrestrial ecosystems begins to grow exponentially. And although animal life on land is still very limited at this time, it is here that the foundation is laid for future grand interactions between plants and herbivores, between pollinators and flowers. This seemingly simple invention, xylem, became one of the most important steps in the great conquest of the continents. The presence of this internal delivery service meant that plants were no longer constrained by the need to keep their photosynthetic parts close to those that depended on them. Roots, which had never seen sunlight and were unable to produce their own food, now received a constant flow of energy from their above-ground parts. This allowed them to grow more vigorously, extending their reach deeper into the soil, expanding their search for water and minerals. Shoots also benefited, receiving a powerful boost for growth and strength. New branches and reproductive organs received all the energy they needed for vigorous development. The result, before our very eyes, is the birth of a perfectly balanced and efficient organism, all parts inextricably linked by vascular channels transporting water, minerals, and energy. The fossil record is reluctant to reveal these secrets. The soft, living tissue of phloem decomposes much faster than tough xylem, making its remains a rarity for paleontologists. However, in unique deposits from the Silurian and Devonian periods, scientists have been fortunate to discover clear imprints of vascular bundles, irrefutably proving the presence of both transport systems. The arrangement of these bundles in ancient branching stems confirms that the delivery of water and sugar occurred simultaneously, supporting a level of rapid growth unimaginable in earlier eras. These fossils are witnesses to a great transition from small, scattered pioneer shoots to vigorous plants capable of forming dense thickets. These new green expanses occupied vast territories and forever changed the face of the planet. The ecological consequences of the emergence of phloem were truly colossal. Thanks to the efficient distribution of sugars, plants were able to invest surplus resources in their growth, going far beyond mere survival. They could now produce more spores, grow taller than their competitors, and significantly extend their lifespans. This ability to dynamically redistribute energy gave them incredible flexibility and adaptability to changing conditions. Imagine, when the sun shines brightly, leaves produce excess sugars, which are immediately released downward, stimulating vigorous root growth. And if a rich nutrient deposit is discovered in the soil, the roots begin to grow vigorously, which, in turn, allows shoots to reach even higher toward the sky. This delicate coordination turned plants into sensitive, adaptive organisms capable of thriving in diverse locations. The development of phloem also changed the very architecture of plants. Branching becomes much more complex and sophisticated as each new branch is now guaranteed to receive the resources necessary for its growth. While early vascular plants simply divided their stems in two, now, with the support of phloem, lateral branching becomes possible. This leads to an explosion of plant forms. Denser canopies emerge, more effectively capturing sunlight and, equally important, casting dense shadows on the ground. Competition for light changes the rules of the game, creating new conditions for life under the canopy of these first forests. The microclimate created by dense vegetation cools the soil, helps it retain moisture, and creates an environment favorable to the survival of other organisms. Thus, phloem indirectly changes the very foundations of ecological interactions, allowing plants to grow not only upward, but also outward, capturing space. Another crucial consequence of this evolutionary breakthrough was the ability to more efficiently support reproductive organs. Sporangia, the spore-containing sacs located at the tips of stems, required enormous amounts of energy for their development and maturation. Now, the phloem could supply these vital structures with sugars directly from photosynthetic factories, ensuring a stable and abundant production of spores. This reliability dramatically increased reproductive success, increasing the chances that spores would be carried by the wind over vast distances and successfully colonize new territories. It was this increased reproductive efficiency that drove the rapid spread of vascular plants across all continents. The very biochemical composition of the sap flowing through the phloem facilitated the creation of new ecological relationships. After all, it contained not only sugars, but also amino acids, hormones, and signaling molecules. All these compounds were involved in regulating plant growth and protecting plants from stress. Millions of years later, this nutritious sap would attract hordes of insects and other animals, laying the foundation for the formation of the most complex terrestrial ecosystems we know. But even in these early stages, the presence of such a nutrient-rich transport network opened new horizons for interaction. Although animal life on land was still extremely limited, the phloem already enhanced the influence of plants on the soil. By supporting larger bodies and deeper root systems, vascular plants accelerated the weathering of rocks and the accumulation of organic matter. The soils beneath them became thicker and more complex, developing horizons that, like annual rings, recorded cycles of growth and decay. These new soils were able to retain significantly more water, protecting them from erosion and supporting far more diverse microbial and fungal communities. Thus, plant development and soil formation became inextricably linked in a single process of coevolution, with each enhancing the other. Looking at the global picture, the evolution of phloem contributed to a significant reduction in atmospheric carbon dioxide levels. Larger plants with longer life cycles absorbed much more carbon through photosynthesis and reliably locked it away in their woody tissues. When these plants died, the carbon was slowly stored in soils and sediments. Over millions of years, this process led to a global reduction in greenhouse gas concentrations, which in turn contributed to the overall cooling of the Devonian climate. Thus, the technology that allowed plants to grow larger indirectly influenced the climate of the entire planet. Visually, the landscapes conquered by these new plants appeared far more structured and complex than before. Clusters of tall stems rose above the ground, branching and creating intricate patterns against the sky. They grew in number, forming dense thickets along streams and in river floodplains. The ground beneath them was immersed in shade for the first time, strewn with fallen stems and the first leaves, which, as they decayed, enriched the soil. At higher elevations where nothing but mosses could previously survive, islands of vascular vegetation now appeared, able to survive thanks to an efficient internal system of resource allocation. Gradually, step by step, the face of the continents became increasingly green and diverse. The combination of xylem and phloem also allowed plants to withstand the vagaries of their environment. When water was abundant, xylem canals transported it upward in vast quantities. When light was abundant, phloem distributed excess sugars, directing them toward growth. And during periods of scarcity, this system helped balance resources, supporting only the most essential functions. This resilience allowed plants to survive in climates that constantly fluctuated between wet and dry seasons, between sunny and cloudy days. Vascular tissues made plants less vulnerable and far more durable components of the Earth's biosphere. On the great journey of land colonization, the emergence of this sophisticated internal circulatory system marked the completion of a cycle that forever united plants from their deepest roots to their highest shoots. Imagine a true revolution taking place within these primitive stems. A highly complex internal transport system emerges, permeating the entire plant from root to tip. These are the arteries and veins of the plant kingdom, known to science as xylem and phloem. They enable organisms to reach unprecedented sizes, reproduce efficiently, and exert a long-term influence on the entire ecosystem. The emergence of this conducting system paves the way for the creation of gigantic and complex plants that will one day become the absolute masters of the land, alter the composition of the soil, and even influence the atmosphere of the entire planet. The conquest of continents is no longer just a timid attempt to gain a foothold at the water's edge. It is a confident, relentless advance, fueled by the quiet streams of life-giving moisture flowing through these inner vessels, streams that forever bind earth and sky into a single living network. But here's the paradox. Having conquered land, plants faced a fundamental problem that threatened to halt their entire expansion: the problem of reproduction. In their natural environment, their reproductive cells, gametes, could swim freely, finding each other for fertilization. On land, however, this process turns into a death trap. The hot sun and dry wind are merciless killers of fragile reproductive cells, and nature finds a brilliant, almost fantastical solution: spores. These aren't just cells. They're veritable armored time capsules surrounded by a super strong shell. Their coating consists of sporopollenin, one of the most stable organic compounds known to science. These microscopic travelers form in special capsule-like structures called sporangia, located at the tips of stems. And then comes the decisive moment. Mature sporangia, like tiny catapults, burst, releasing an invisible cloud of thousands or millions of spores into the air. This can occur due to a change in humidity or simply a random mechanical shock. This protective armor allows the spores to survive everything: scorching drought, damaging ultraviolet radiation, and long journeys through the air in search of a suitable place for new life. This incredible innovation opens up entirely new horizons for the plant world. The possibilities for colonization increase thousands of times. Now the offspring no longer need to huddle at the base of the parent plant. The wind, once an enemy, becomes their greatest ally, carrying spores across rivers, mountains, and valleys to new, unexplored territories. Their microscopic size makes them ideal flyers, and their colossal numbers greatly increase the chances that at least a few will find a home and start a new colony. This ability to disperse en masse becomes key to survival in constantly changing landscapes, preventing populations from becoming trapped in isolated oases. And we have irrefutable evidence of this quiet expansion. Paleontologists studying deposits from the early Silurian period are finding fossilized clusters of spores, microscopic evidence discovered hundreds of kilometers from ancient coastlines. The very structure of the sporangia is a masterpiece of evolutionary engineering, perfectly adapted to life on land. In the earliest plants, these spore-bearing capsules formed at the very tips of branches raised high above the ground. This position ensured maximum exposure to air currents. In other species, they were located along the stems, gradually releasing their precious cargo. Rising as high above the surface as possible was the primary goal. After all, the higher the plant, the stronger the wind, and the further it will carry future life. And here we see how one evolutionary innovation reinforces another. The very same vascular tissue that delivers water to the tops now serves as a strong framework, allowing the plant to reach for the sky and more effectively disperse its spores. Each of these spores is a potential new colony, ready at any moment to give rise to a green shoot, even in the most lifeless soil. Their incredible resilience is ensured not only by their tough shell, but also by their ability to enter a state of deep, suspended animation. They can remain dormant for decades, even centuries, awaiting only one thing: a drop of moisture and suitable soil to awaken to life. This wait-and-see strategy is invaluable in a world where rainfall is irregular and the soil quickly dries out. The spores simply bide their time, not wasting energy during unfavorable periods. It was this tactic that allowed the first plants to establish themselves on land, despite all the harsh challenges. For paleontologists, fossil spores are a veritable treasure trove of information. Their extremely strong walls are perfectly preserved in sedimentary rocks, turning into perfect microfossils. These tiny artifacts of the ancient world open a window into the past, allowing us to trace the entire evolutionary path of plants. Fossil spores are unique witnesses to the evolution of the planet's plant kingdom. They reveal how, over millions of years, their shapes became increasingly complex, evolving from primitive spheres to intricate patterns. These communities, though they cannot be called true plants, are already beginning to shape the landscape, defining the appearance of this ancient world. They greedily capture the sun's rays, bind the loose soil together, and accumulate precious islands of organic matter. Over time, these living carpets accomplish something incredible. They halt the movement of sediment, bringing stability to what was once perpetual chaos. In these humble structures, we can discern the very first steps toward the creation of a true soil cover. When ocean waves retreat, exposing the moss, they dry out and become covered in a network of cracks. But their strength is astounding. Their incredible resilience stems from a simple yet effective chemistry. Their secretions form sticky layers around microscopic fibers. Tiny grains of sand and shell fragments become firmly entangled in these networks, strengthening the bond and transforming the fragile film into a durable shell. In tidal pools, where water lingers for long periods, the layer of microbes becomes noticeably thicker and denser. Complex communities gradually build upon one another, creating a hard, almost rock-like surface. Each new layer adds strength to the entire structure. On countless coastlines of that era, these patches become the first outposts of life, desperately clinging to the land. But beyond their physical presence, these mats begin to transform the environment. The sheer number of spores found in geological layers speaks volumes. It confirms that in certain eras, plants were widespread, even if no other larger fossils of them remain. The study of these microscopic remains has become one of the key tools for reconstructing the history of land conquest. The discovery of spores in rocks formed far from ancient seas demonstrates the incredible effectiveness of wind as a means of spreading life across continents. The impact of this process on the environment was colossal. Spores created gigantic networks of plant populations across vast territories, linking the communities that would otherwise have been doomed to isolation. This connectivity increased genetic diversity, making plants more resilient and adaptable to different soil types and climates. Furthermore, spores facilitated the rapid restoration of ecosystems, repopulating areas devastated by floods or erosion. Spore formation also plays a central role in the life cycle of these pioneers. This cycle alternates between two generations. One produces gametes, which still require water for fusion. But after fertilization, another generation, the sporophyte, emerges, creating sporangia for aerial dispersal. On land, it is the sporophyte that becomes an increasingly large and prominent part of the plant, supported by robust vascular tissue and fueled by photosynthesis. This evolutionary shift demonstrates how crucial elevating sporangia above ground has become for their efficient dispersal. And in the future, the sporophyte will become the dominant form in the life cycle of all higher plants. But the influence of these microscopic particles extends far beyond biology. It alters the very geology of the planet. Billions and trillions of spores settling on the ground become part of sedimentary rocks. Their walls, enriched with sporopollenin, form decay-resistant organic matter. They saturate the soil and rocks with carbon, permanently integrating themselves into the global carbon cycle. Sometimes, Spore clusters are so dense that they form distinct dark layers in geological sections. These horizons are evidence of eras of massive blooms and spore dispersal, possibly linked to seasonal cycles or particularly favorable climates. The incredible durability of these microfossils allows them to survive for hundreds of millions of years, allowing us to study the activity of ancient plant life. Let's travel back to that world, 430 million years ago. Before us stretches the landscape of the Silurian and early Devonian periods. Small groves of upright shoots dot the damp lowlands. An invisible haze hangs over this silent land. It's not dust, it's an endless silent rain of spores that these plants release into the air. These processes, invisible to the eye, have a colossal impact on the planet. The Earth is literally strewn with these tiny seeds of life. Most will die, but some, exposed to the moist environment, will germinate, giving rise to new plants and expanding the green canopy. This cycle repeats endlessly, generation after generation, and each time, countless spores, like a silent shower, settle to the ground, carrying within them the potential for new life. The wind is the mastermind behind this process. Air currents, constantly changing in strength and direction, carry spores across the landscape. Some will land close by, while others will drift through the air for many kilometers. This process seems chaotic and inefficient, as spores land in both good and bad spots. But their incredible numbers more than compensate for this randomness. It's a strategy based on the brute force of numbers, producing millions of tiny chances instead of a few large ones. Early conquest of land is a game of probabilities, not precise calculations. Yet, despite this incredible breakthrough, ancient plants still bear the shackles of their aquatic past. Although spores travel through the air, the most important act, fertilization, still requires water. Even the thinnest film of dew or rainwater is necessary for male cells to swim to female cells. This dependence firmly binds plants to humid habitats, even though spores allow them to colonize drier regions. It will take millions of years before new evolutionary adaptations break this chain. But at this stage of development, we are witnessing a remarkable hybrid strategy, harnessing the power of the airy oceans for travel, but returning to a tiny drop of water for the most intimate act, the creation of new life. Thus, spores become a key invention at this stage of evolution. Their durable walls, ability to remain dormant, and wind-borne dispersal ensured the continuity of plant life on land. They paved the way for the colonization of new worlds, facilitated the exchange of genetic material, and became an invaluable part of the fossil record. Although spores are small and inconspicuous, they were true engines of progress, helping plants begin their triumphant march across the planet. They were the seeds of possibility. Not yet true seeds, but already the first, and perhaps most important, step toward their emergence. This was a decisive step toward absolute dominance in the plant kingdom. As tiny spores, like dust, spread across the globe, conquering new territories, nature itself prepared for the next great leap. The landscapes of ancient Earth were changing, and survival strategies had to change with them. Let's fast forward millions of years to the era when the plant world was taking its first confident steps. Initially, everything was simple and efficient. Plants produced spores, identical to each other. Each of these microscopic particles was a universal soldier, capable of giving rise to new life, carrying both male and female reproductive organs. This strategy, known as homospory, worked remarkably well, but as plants colonized the planet, more and more challenges arose. It soon became clear that versatility wasn't always the best path. Nature began experimenting, and this experiment led to a revolution. Plants realized it was much more efficient to divide the responsibilities. This is how two completely different types of spores emerged. Imagine this division of labor. On one side were the large, massive megaspores. These were veritable arks, brimming with nutrients to support future female organs. Only a few were produced, but each one was essential for the survival of the offspring. On the other side were countless myriads of microspores, light as feathers. Their job was to travel, carrying the male principle as far as possible, covering vast territories. This ingenious invention, known as heterospory, became a turning point in evolution, paving the way for the emergence of seeds. We find the first evidence of this revolution in late Silurian deposits, and by the Devonian, it was already in full swing. Fossils of ancient plants such as lechophytes and progymnosperms bear clear signs of this division. Paleontologists find both large and small spores in the same layers. Large megaspores, few in number, but rich in resources, gave the future embryo a powerful start, providing it with everything it needed during the early stages of growth. Meanwhile, small microspores were produced in incredible quantities, their sole purpose being dispersal and fertilization. This specialization proved incredibly successful. Instead of attempting to perform two functions at once, each spore type focused on one, dramatically increasing the chances of reproductive success, especially in a world full of dangers and fierce competition. The development of heterospory triggered a chain of consequences. By concentrating resources in megaspores, plants gave their offspring a much better chance of survival. With their own nutrient reserves, megaspores could survive unfavorable conditions and await the ideal moment to germinate. Microspores, thanks to their lightweight and abundance, enabled incredible genetic exchange, covering vast distances. This combination of reliability and mobility made plant populations much more resilient. Over time, through a long evolutionary race, these two types of spores would evolve into what we know as egg cells and pollen, the key components of seed plants. But this transition wasn't instantaneous. For millions of years, the two reproductive strategies coexisted side by side. Homosporic plants continued to dominate many ecosystems, covering the earth with a carpet of identical spores. But heterosporic plants, though in the minority, gained a huge advantage in certain environments where protecting offspring and efficient resource use played a crucial role. The Earth's rock record clearly depicts this picture of coexistence, but it also suggests that heterospory was the future. It was an evolutionary springboard that prepared plants for the creation of seeds, the ideal tool for conquering land. The ecological consequences of this innovation were colossal. Large megaspores allowed plants to colonize drier and more inhospitable lands where water was not readily available. They also marked the first historical manifestation of parental care in the plant kingdom. Plants stopped dispersing their energies by producing countless weak offspring and focused on producing a smaller but much stronger and more prosperous number. This was a shift from quantity to quality. Microspores, in turn, ensured fertilization over vast areas. The interaction of these two strategies made reproduction possible in the most diverse and complex environments. Paleontologists were incredibly lucky. Megaspores were preserved in fossil form with astonishing clarity. Some of them reach a millimeter in diameter and are visible to the naked eye. Their surface is often covered with complex, intricate patterns, a kind of armor that protected the precious contents. Microspores, of course, are much smaller, but they are found in the same layers in enormous quantities. This is irrefutable evidence that both reproductive systems operated simultaneously in the same ancient forest. The emergence of heterospory also changed the plant life cycle itself. Instead of a single universal gametophyte, which would produce both male and female cells, two highly specialized ones now emerged. The female gametophyte developed within a protected megaspore and the male within a tiny microspore. This division dramatically reduced the likelihood of self-fertilization, promoting genetic diversity. This was another step toward the dominance of the sporophyte, the plant form we're accustomed to seeing. All these changes presaged the emergence of seed plants, where tiny gametophytes are safely ensconced within the tissues of the mother organism. But the influence of heterospory wasn't limited to reproduction. Large, resource-rich megaspores that failed to germinate became valuable organic material. They enriched the soil with carbon, facilitating its formation. The difference in spore size also influenced their dispersal. Microspores, carried by the wind, floated beyond the horizon, while heavier megaspores fell nearby. This created a unique colonization pattern: dense thickets around the parent plants, connected by invisible threads of genetic exchange with distant populations. Interestingly, the emergence of heterospory often coincides with the increasing complexity of plant structure. Species that mastered the production of two types of spores often had more developed vascular systems, xylem and phloem, that supported their stems and roots. Reproductive and structural innovations went hand in hand, allowing these plants to conquer ever-new ecological niches, from swamps to mountain slopes. Let's imagine the landscape of that era. Outwardly, it might not look much different from the forests dominated by homosporous plants, but if you look closely, you'll see the difference. Plants bearing sporangia periodically release clouds of spores into the air, but this cloud is not uniform. The heavy megaspores settle almost immediately at the base of the parent, creating a dense colony of offspring around it. Meanwhile, the light microspores are carried by the wind on long journeys, knitting together disparate patches of forest. Generation after generation, this dual strategy ensured both local stability and regional unity. The long-term impact of this revolution is simply astounding. During the Silurian and Devonian periods, heterospory was just one of many evolutionary experiments. But it laid the foundation for the emergence of seeds. The seed, in essence, took all the best features of heterospory: a protected embryo, a huge supply of nutrients, and a durable seed coat. And most importantly, it completely freed plants from their dependence on water for reproduction. Thus, heterospory can be seen as a crucial transitional stage, a bridge between primitive spore-based reproduction and the incredibly complex seed-based systems that would eventually conquer the entire planet. At this stage in Earth's history, it was still an experiment, but the fact that it arose independently in several different evolutionary lineages speaks to its enormous adaptive value. Evolution often finds similar solutions to the same problems, and the repeated emergence of heterospore is the best proof of this. The seeds had not yet been born, but their blueprints could already be discerned in this ingenious division of spores, in a new resource allocation strategy, and in the growing specialization of reproductive roles. Heterospory became a key innovation that made plants more flexible, resilient, and efficient. It increased their chances of survival, increased genetic diversity, and ultimately paved the way for the advent of a new era, the era of seed plants. Here, at the dawn of time, a quiet but momentous revolution unfolded that would forever change the face of our planet. Plants became leaders in the conquest of new, previously unexplored landmasses. It was a subtle turning point, an almost invisible change in spore size that ultimately predetermined their entire subsequent evolution. The future of all ecosystems and the entire trajectory of life on Earth depended on this seemingly insignificant process. Let's fast forward to the early Devonian period. It is here, in this ancient world, that plants begin to arm themselves with new, far more sophisticated tools for survival. They create shade, lowering surface temperatures during hot hours and slowing evaporation. They trap precious moisture in their films, forming tiny oases, microscopic worlds that are strikingly different from the bare, scorching rocks around them. In these protected refuges, algal spores and cells have a chance to survive longer without being completely submerged. This temporary refuge vividly demonstrates how life begins to simmer at the very boundary between sea and land, exploring the limits of what is possible beyond eternal submersion. Ordovician coastlines are places of constant struggle. The relentless rhythm of the tides, fierce storms, and ever-shifting sediments keep the surface in constant flux. Waves tirelessly churn the sand. The wind carries salt spray, and puddles appear and then vanish without a trace. And yet, despite this perpetual chaos, microbial mats demonstrate remarkable stability. They provide a reliable support for long, thin threads of living organisms. In this volatile world, the very ability to stabilize becomes a tremendous achievement. The mats bind loose particles into a strong crust, significantly reducing erosion and allowing organic matter to accumulate. Over hundreds of thousands of years, these accumulations alter the very structure of the coastal soil, transforming loose sediments into compacted surfaces teeming with life. Occasionally, astonishing stromatolite-like structures form here, rising slightly from the flat landscape. They develop true roots laced with vascular tissue and develop increasingly complex reproductive strategies. A veritable arms race unfolds in the wet, marshy lands and along the banks of ancient rivers. To survive and dominate, they must become larger, taller, and stronger. Some species begin to develop an entirely new material, woody tissue. This allows them to soar upward, becoming stronger and more massive than anything before them. The first ancestors of forests appear before us. These plants, often reminiscent of giant tree horsetails or milkweeds, along with the first gymnosperms, begin to take over the landscape. Their mighty stems reach several meters into the sky, and their branches spread out, creating shade above the ground. Of course, these communities do not yet resemble modern forests, but they represent a colossal step forward, from scattered green islands to continuous, dense thickets that transform both land and water. The secret to their success lies in their woody tissue. This revolutionary material, composed of recycled xylem reinforced by the durable polymer lignin, performs two vital functions. It provides reliable mechanical support and simultaneously functions as a transport system for pumping water to enormous heights. The strength of this tissue allows these ancient trees to withstand the elements. Under fierce gusts of wind and during devastating floods, they continue to grow vertically, surviving where their more primitive ancestors would have been broken and destroyed. As these giants rise higher, they begin to intercept ever more sunlight, casting a dense shadow on the ground at their base. Thus, for the first time in the planet's history, a multi-layered habitat is formed. Now below, in the semi-darkness, only those plants that have adapted to low light can thrive. Those that desperately need bright sunlight find themselves at a disadvantage. The very structure of these proto-forests triggers a process of ecological stratification, a key feature of all complex terrestrial ecosystems of the future. Wetlands are becoming the epicenter of this green revolution. They provide plants with abundant water and nutrients, essential for the growth of such giants. By sinking their roots into the soft, waterlogged soil, these plants, like engineers, stabilize sediment, slow erosion, and dramatically alter the hydrology of entire regions. Water levels, which previously fluctuated chaotically from season to season, are now stabilized by resilient green spaces. Vegetation, like a dam, slows river flows, creating vast marshy areas where water accumulates. This organic, rich, viscous environment becomes a gigantic reservoir. Wetlands become powerful carbon sinks. They capture and preserve plant material, which decomposes incredibly slowly in the anoxic conditions of the wetlands. Millions of years from now, these ancient deposits will transform into enormous coal seams, a silent testimony to the great age of forests. But their influence isn't limited to the earth. The growth of giant vegetation triggers a chain reaction of atmospheric changes. Taller plants absorb colossal volumes of water from the soil and evaporate it into the air, directly affecting regional humidity and precipitation. Their photosynthetic activity leads to a much more efficient absorption of carbon dioxide from the atmosphere, which, in turn, triggers a global process of long-term climate cooling. Gradually, atmospheric oxygen levels rise, fueled by the accumulation of organic matter in soils and sediments. To us, this process seems incredibly slow, but on the scale of planetary history, it plays a decisive role. Millions of years of patient plant activity have transformed the Earth's atmosphere, paving the way for the future flourishing of animal life on land. The fossil record contains evidence of this great transformation. Fossil remains of ancient plants, such as Archaeopteris, considered one of the first true trees, tell us that vast forest ecosystems already existed in those distant times. Archaeopteris combined a powerful woody trunk with branches covered in dense foliage, and at its peak, it reached a height of 10 meters, a true skyscraper by the standards of the time. Its appearance in the fossil record marks a crucial stage in the development of forests. Nearby, giant club mosses and horsetails formed impenetrable thickets of tall, jointed trunks. And although these plants had not yet invented seeds and reproduced through primitive spores, their enormous size and abundance forever transformed the face of the planet. They completely dominated the swampy plains, creating the first recognizable forests in Earth's history. The ecological consequences of their appearance were truly monumental. Powerful root systems penetrated deep into the ground, breaking down rock and creating soil. Their spreading crowns created a unique microclimate, cooling shaded areas and retaining precious moisture near the surface. Fallen leaves accumulated on the ground, forming a thick layer of organic debris that enriched the soil and created an ideal environment for fungi, primitive insects, and other decomposers. For the first time, terrestrial ecosystems are acquiring a vertical structure with clearly defined layers of light, shade, and soil. This complexity is fueling an explosion of biodiversity and laying the foundation for future evolutionary breakthroughs. Forests also have a colossal impact on the water cycle. By slowing runoff and strengthening soils, they reduce the amount of silt in rivers, making the water cleaner and altering the entire water balance, creating more favorable conditions for life downstream. By evaporating water, forests promote the recycling of atmospheric moisture, leading to more uniform precipitation. This feedback between vegetation and climate was something entirely new in Earth's history. Thus, the emergence of forests is not simply a biological event, but a crucial geoecological one. These planetary changes occurred unevenly. Forests emerged where conditions were most favorable, on broad river floodplains, coastal lowlands, and deltas where moisture was abundant. At higher elevations, where soils were thinner and drier, low-growing plants continued to dominate. However, over time, the evolutionary advantage of woody tissue and height allowed forest giants to expand beyond their swampy habitats and gradually colonize drier lands. This expansion was slow but steady, driven by the strength of roots, vascular tissue, and canopies capable of surviving in the most challenging conditions. The fossil record records this progress. In early Devonian deposits, forests appear as isolated, scattered pockets in the lowlands. But by the end of the Devonian and into the Carboniferous, they cover vast territories, and their remains are preserved in the form of massive coal seams. These fossils are the best evidence of how the green world conquered the planet, recording the moment when plants radically changed the entire biosphere. The emergence of forests was one of the key events of the Paleozoic era, comparable in its consequences to the emergence of animals on land. The new conditions also influenced plant evolution itself. Taller species could disperse their spores from greater heights, facilitating their dispersal over vast distances. However, the dense canopy also created new problems. Spores trapped in deep shade had no chance of survival. This evolutionary pressure pushed plants to further adaptations, ultimately leading to the development of seeds and pollen, far more reliable and specialized reproductive strategies. Forests became not just a home, but also a harsh testing ground, determining the course of plant evolution for millions of years to come. The emergence of giant forests also changed the animal world. Insects, which had already begun to colonize land, found countless new ecological niches here, on the surfaces of leaves, in bark, and in shaded soil. Organisms that fed on dead organic matter flourished, feasting on fallen leaves and tree trunks, giving impetus to the development of the first complex food webs on land. It was in these conditions that the first land vertebrates emerged. They migrated from rivers to swampy forests, where they found both food and shelter in abundance. Thus, it was plants that created the stage on which animals could play out the drama of their conquest of land. Imagine the spectacle: ancient Devonian forests striking a striking contrast to the previously lifeless landscapes. Instead of low thickets, tall, strange trunks rise meters into the air. Sunlight, filtering through the dense canopy, casts a strange, dappled shadow on the ground. Streams meander and dark pools spill among mighty roots clinging to the banks with a death grip. The air is humid and thick, saturated with the vapors of rotting organic matter. For the first time on Earth, conditions resembling a true forest have appeared, albeit a more primitive one than those that will replace it. The significance of these forests goes far beyond their physical presence. They inhaled carbon dioxide, exhaled oxygen, and forever entombed carbon in sediment, changing the atmosphere on a planetary scale. By stabilizing soils and creating a milder climate, these forests became an integral part of the Earth's global ecosystem, engineers who laid the foundation for all life that would come after them. Let's fast forward to that distant world where plants are revolutionizing life. By creating multi-layered vertical worlds and incredibly complex living conditions, they are completely reshaping ancient ecosystems. With the emergence of the first forests, an entirely new chapter in the Earth's history begins. Now, plants are not just desperately clinging to life on land. They are beginning to dominate it, shaping the future of all living things for millions of years to come. As ancient forests conquer swampy lowlands and river valleys, their dominion over the landscape becomes absolute. Imagine powerful root systems that don't simply cling to the soft soil and shallow water. They bite into riverbanks like living anchors, tightly binding sediments that were once carried away by each flood. These tangles of roots act as a gigantic reinforcing mesh, stabilizing riverbeds, preventing them from wandering chaotically across the plains as they did in previous lifeless eras. The roots bind billions of particles of silt and sand that were carried downstream in muddy streams, forcing the rivers to carve narrower, more permanent, and deeper paths. Over millennia, this seemingly imperceptible process gives rise to entirely new ecosystems and dramatically transforms entire continents. This stabilization affects vast drainage systems, creating a permanent network of waterways. Old riverbeds, oxbow lakes, and wide floodplains are transformed into multi-layered fertile soils brimming with organic matter. The plants that grow on these lands become true engineers, sculptors, changing the face of the planet. We can see the mechanical influence of these living networks on rivers with our own eyes by examining the geological record. Sedimentary rocks from the Devonian period differ strikingly from those of earlier times. They exhibit a distinct layered structure, where the finest silt is forever sealed among the fossilized imprints of ancient roots. This paleontological evidence reveals a picture of the total stabilization of the world, something unimaginable in previous eras. Rooted soils bound by life desperately resist erosion. They preserve fertile horizons where invaluable organic matter accumulates year after year, century after century. In comparison, bare soils, unprotected by plants, are washed away by the first rainstorms, leaving nothing but stone. Over time, the difference between green oases and open, lifeless landscapes becomes colossal. Plants leave an indelible imprint of their presence in the stone, and their roots play a central role in this monumental process. But their influence isn't limited to mechanics alone. Plants fundamentally alter the chemical composition of rivers. They release organic acids into the soil and, like pumps, absorb minerals. These substances, rising from the depths, transform the composition of groundwater, which in turn feeds streams and rivers. As a result, the chemistry of river water itself undergoes dramatic changes. The concentration of dissolved ions, such as calcium and magnesium, increases sharply, making the water harder. At the same time, root systems greedily absorb nutrients, reducing their concentration in river runoff and thereby reducing the load on marine ecosystems. These global chemical shifts affect all bodies of water and life downstream, altering the delicate balance of organisms in rivers, vast deltas, and even shallow coastal seas. The power of plants extends far beyond the places where they grow, reaching the very depths of the ocean, where the rivers they have transformed flow. Roots, by holding the soil in place, dramatically reduce the amount of silt and sand carried into the sea, and this seemingly insignificant change has colossal consequences for marine life. In earlier eras, the enormous masses of sediment washed into the ocean were a curse for coastal ecosystems. Shallow seas were often shrouded in a murky cloud that blocked sunlight and killed photosynthetic organisms on the seabed. But now, with rivers carrying cleaner, clearer waters, light penetrates much deeper, nourishing underwater seagrass beds and organisms building the first reefs. This shift triggers an explosion of productivity and biodiversity in coastal waters. Thus, stabilizing rivers on land indirectly leads to a flourishing of life in the ocean, creating an inextricable link between terrestrial vegetation and marine ecosystems. The creation of stable, regularly flooded zones leads to the emergence of entirely new terrestrial worlds. Between river channels, fertile soil accumulates, generously enriched with organic matter from fallen leaves and dead stems. These floodplains support lush, dense vegetation, forming a complex mosaic of marshy swamps and riparian forests. In such conditions, biodiversity literally explodes. Countless arthropods swarm among the fallen leaves. Fungi break down dead organic matter. And then the first vertebrates, our distant ancestors, dare to venture onto dry land in search of food and reliable shelter. These layered formations are the result of microorganisms that capture sand grains and cement them together with calcium carbonate. In quiet backwaters, they can persist for quite some time, forming low ridges that can withstand the onslaught of waves far more effectively than bare mud. These living barriers weaken the force of tidal waves and create additional protected spaces behind them. Here, the smallest particles settle, enriching the environment and preparing a springboard for further colonization. It is in these secluded corners that nature's earliest experiments with terrestrial life can finally reveal their true potential. Chemical processes within the mats add another dimension to their impact on the planet. Photosynthesis helps reduce carbon dioxide levels in the local environment, altering its acidity and releasing oxygen as a byproduct. While overall atmospheric oxygen levels remain negligible, their concentrations can increase significantly within the mats themselves. These oxygen pockets support other organisms, fostering biodiversity on the fringes of the aquatic world. This slow gas exchange also influences mineral deposition. Calcium carbonate crystallizes around living filaments, further strengthening the mat structure. Through these processes, biological activity becomes increasingly diverse and stable. Life doesn't simply survive, it imperceptibly but irreversibly alters the very rock on which it lives. Floodplain plains become epicenters of evolution, veritable cradles for new forms of life. All these ecological innovations, through which life adapts to previously unseen conditions, are made possible only by the stability provided by vegetation. But the influence of roots isn't limited to river valleys. They have an equally significant impact on hillsides and uplands. By holding soil in place on slopes, they minimize the risk of landslides and erosion of topsoil. Rainfall, which previously washed everything in its path down into valleys in torrents, is now absorbed into the ground, penetrating deeper and accumulating. This infiltration sustains plant life during dry periods and ensures the constant supply of rivers. The entire hydrological cycle of the planet becomes smoother and more moderate, dramatically reducing the likelihood of catastrophic floods and severe droughts. By stabilizing slopes and regulating water levels, plants alter the dynamics of entire continental divides. The long-term consequences of this root revolution are clearly visible in stratigraphy, the study of rock layers. Sedimentary basins beginning in the Devonian period exhibit far fewer chaotic jumbled deposits and more ordered tranquil sequences, reflecting the steady accumulation of material. Thick coal seams appear and spread widely. They are nothing more than the compressed remains of ancient plants preserved in stable, swampy ecosystems. This geological evidence irrefutably demonstrates the long-term planetary influence of roots on all processes occurring on the Earth's surface. Thus, the spread of vegetation leaves its signature on the body of the planet, imprinted in the rock for hundreds of millions of years. Roots also dramatically improve the vertical structure of the soil itself. Penetrating deep, they create a network of channels that facilitate air circulation and water infiltration. When a root dies and decomposes, it leaves behind pores that harbor billions of microorganisms and store moisture. This greatly increases soil fertility, which in turn allows larger and more vigorous plants to grow. And the larger the plants, the deeper and stronger their roots. This initiates a cycle that, over time, transforms a thin layer of dust on rocks into deep, structured, and fertile soils. These changes support ecosystems that become increasingly complex and resilient. The stabilization of rivers and soils also has a profound impact on the global carbon cycle. By holding sediment in place, roots prevent organic matter from being transported to the oceans, where it would otherwise be buried. As a result, much more carbon remains on land, locked up in soils and peatlands. Over millions of years, this enormous carbon reservoir contributes to a global decline in atmospheric carbon dioxide levels, reinforcing cooling trends that alter the planet's climate. Simultaneously, the rapid expansion of photosynthesis leads to increased oxygen levels, altering the composition of the atmosphere in a way that makes possible the spread of increasingly larger and more complex animals onto land. Plants, through their invisible roots, act as powerful agents of planetary change. Visually, the landscapes of that era, with their stabilized rivers, are strikingly different from what came before. River channels no longer wander chaotically across the plains, but flow along clear, stable routes framed by green corridors of dense vegetation. Floodplains are covered with a lush carpet of greenery. The soils are dark and moist with organic matter, and the hillsides, entwined with roots, stand firm even after the heaviest rains. The river deltas in the lower reaches appear more powerful and fortified, their sediments securely held by a living armature. The contrast with the barren, parched, and constantly changing landscapes of the past is simply stunning. A world that was once fickle and unstable becomes constant, predictable, and fertile, all thanks to the invisible work of roots. Roots not only shape the landscape, but also create the conditions for ecological continuity. Stable soils allow different plant species to succeed each other over many generations, accumulating organic matter in the same place. This continuity supports the development of incredibly complex ecological systems. Communities in which species begin to depend on each other first form in the Devonian period. Fungi, arthropods, and the first vertebrates exploit this new stability, creating food webs that are passed down from generation to generation. Habitat stability becomes no less important than its fertility, allowing ecosystems to evolve, deepen, and become more efficient. Geologically, the Devonian period is sometimes called the Age of Fishes, but that's not entirely accurate. It could just as easily be called the Age of Roots. The development of root systems was one of the most fundamental transformations in the history of our planet. By stabilizing rivers, soils, and slopes, roots altered landscapes, hydrology, and even the composition of the atmosphere. Their influence extends from the smallest pores in the soil to the global climate, forever linking the fate of land, water, and air. Plants, through their roots, became the invisible architects of the Earth's surface. In summary, it's safe to say, taming rivers and landscapes with roots is a key stage in life's conquest of land. What began with the finest, barely noticeable rootlets holding together fragile bacterial mats culminated in vast forests that transformed entire continents. Thanks to roots, rivers became cleaner, soils deeper, slopes more stable, and ecosystems richer. The land became more stable, fertile, and habitable. And all this thanks to the quiet, invisible, yet truly titanic work of plants. With their mighty roots, they bind together the entire planetary system. Just imagine how, as the first forests spread across valleys and hills, their power extends far beyond the soil and rivers. Their influence reaches to the sky, changing the composition of the atmosphere. Plants begin to respire on a global scale. They greedily absorb carbon dioxide and exhale life-giving oxygen. Through photosynthesis, nature's greatest miracle, leaves absorb carbon dioxide from the air, which, when reacting with water, is converted into nutritious sugars. As a byproduct of this process, oxygen is released into the atmosphere. In the most ancient eras, this gas exchange was the preserve of modest microbial mats and tiny mosses which had virtually no impact on the world around them. But by the end of the Devonian period, giants emerge. Vast forests of vascular plants with broad leaves and tall, sturdy trunks come into play. Their photosynthesis reaches such colossal proportions that it begins to dictate the entire chemistry of the planet. The process of removing carbon dioxide from the atmosphere is further accelerated by the burial of dead vegetation. Wood tissue, rich in lignin, a natural polymer that makes it strong, decomposes extremely slowly, especially in the anoxic environment of swampy soils. As a result, tons of organic carbon are not returned to the atmosphere, but accumulate in sedimentary rocks, layer after layer. Over millions of years of geological time, some of these carbon stores will turn into coal, forming thick layers that store the energy of ancient forests. This global process of carbon sequestration leads to a reduction in the amount of greenhouse gases in the atmosphere, which, in turn, triggers a long-term trend toward global cooling. Climate simulations show that the Devonian period saw a catastrophic drop in carbon dioxide levels, which coincided perfectly with the expansion of forests. This cooling effect may have triggered the glaciation at the end of the period, demonstrating how life can change not only the face of land, but the planet's climate itself. At the same time, another, no less important process is taking place. Atmospheric oxygen levels begin to rise steadily. They continue to rise because the ancient balance between photosynthesis and respiration is disrupted. When forests cover vast areas, the amount of oxygen they produce begins to significantly exceed the amount consumed by animals for respiration and by microbes for decomposing organic matter. This excess oxygen is no longer bound by anything, and it begins to accumulate in the atmosphere, gradually making it increasingly concentrated. Analysis of fossil soils and other geochemical markers unmistakably indicate that by the end of the Devonian, oxygen concentrations in the air reached much higher values than in the preceding Paleozoic eras. For the animal world, this event was a true revolution. Arthropods, creatures that breathe not through lungs but through a complex system of tubes running through their bodies, received an incredible gift. In a world oversaturated with oxygen, their previous physiological limitations simply evaporated. And then, in the Devonian and subsequent Carboniferous periods, true monsters crawled onto land. We see giant, centipede-like arthropleura and insects reminiscent of dragonflies, but with the wingspan of a modern eagle. Their colossal size is a direct consequence of this oxygen feast. The planet's air became the fuel for gigantism, forever linking the evolution of the atmosphere with the evolution of life on land. The impact of forests on climate was truly multifaceted. Trees transformed into giant water pumps, recycling vast volumes of water, evaporating moisture back into the atmosphere, and directly influencing cloud formation and rain cycles. Dense tree canopies, like umbrellas, held back downpours, allowing the water to slowly flow to the ground and be absorbed by the soil, and powerful root systems managed water filtration and the replenishment of underground aquifers. All these processes made the climate in forested regions more humid and predictable, smoothing out extreme temperature fluctuations and preventing catastrophic droughts and devastating floods. On a global scale, The spread of forests altered established wind patterns, reshaped precipitation patterns, and even interfered with global atmospheric circulation. The Earth was transformed into a highly complex living organism where land and atmosphere became inextricably linked thanks to the new green cover. Moreover, forests radically altered the energy balance of the Earth's surface. Dark green tree canopies interacted with sunlight very differently than bare rock. They absorbed much more solar energy, contributing to localized heat accumulation. However, to avoid overheating, plants evaporated water from the surface of their leaves, a process called transpiration that effectively cooled both the plants themselves and the surrounding air, creating an ideal energy balance. This complex interaction of energy and water flows created intricate feedback loops between vegetation and climate. In some regions, forests began to literally create their own rain, sustaining themselves through local moisture recycling. In others, they significantly reduced surface temperatures by shading the soil and acting as a giant natural air conditioner. These interactions laid the foundation for the formation of Earth's modern climate. It became clear that climate is the result not only of blind geological forces, but also of powerful biological factors. Geological traces of these atmospheric upheavals can be found in the isotopic composition of ancient rocks and, most surprisingly, in the fossils of the plants themselves. It turns out that the density of breathing pores, or stomata, on fossil leaves can tell us about the concentration of carbon dioxide in the ancient atmosphere. The logic is simple. In eras with low CO2 levels, plants had to grow more stomata to more effectively capture this scarce gas. Conversely, when carbon dioxide was abundant in the air, a large number of stomata was unnecessary. Fossil leaves found in Devonian deposits show a clear pattern. Stomatal density gradually increased, which coincided perfectly with the decline in atmospheric carbon dioxide levels. This independent data provides irrefutable evidence that the expansion of forests had a decisive influence on the global climate. Changes in the atmosphere and climate in turn became a powerful driver of the evolution of entire ecosystems. Oxygen-rich air paved the way for the development of increasingly larger and more active animals. A cooler, wetter climate allowed forests to expand into new areas that had previously been too hot or dry. And the stabilization of soils and river systems by root networks further accelerated these trends, creating countless new, favorable habitats. Life on land became increasingly complex, diverse, and interconnected. The emergence of forests is more than just a chapter in the history of botany. It is a crucial milestone in the history of the planet, defining the conditions in which all subsequent life, including us, would evolve. Let's travel deeper into this ancient world to see how its landscapes have changed. The late Devonian landscapes have been transformed beyond recognition. Giant trees now tower over the flooded lowlands. Their rough-barked trunks soar upward, and their branches intertwine to form a dense green canopy. This canopy of leaves casts a dense shadow on the forest floor. The air here is thick, humid, and saturated with oxygen. It literally hums with the buzzing and chirping of the myriad creatures that have found a home here. Rivers, no longer muddy streams, meander calmly between forested banks, their waters cleaner and more transparent. Thick layers of peat accumulate in the marshy lowlands, and on the hills, the first sparse forests cling to more fertile soil. If we look at the planet from above, the continents appear before us as a huge green mosaic, marking the birth of a new era in the history of the Earth, an era of total greening. The long-term consequences of these changes were truly global. Forests played a key role in the dramatic reduction of carbon dioxide levels, which directly affected global temperatures and set the stage for future ice ages. At the same time, they pumped oxygen into the atmosphere, enabling the emergence of giant land animals. They stabilized soils and rivers, forever altering geological processes of erosion and sedimentation. By creating vertical structures and shaded refuges, plants created an incredible diversity of new ecological niches. When storms sweep over coastal plains, giant waves tear the mats to pieces, and their fragments are carried into open water. Some, washed ashore elsewhere, take root and found new colonies, expanding the boundaries of life. Others decompose, enriching the sediment with organic matter. Each such natural disaster reshapes the coastline, but life always finds a way to return. The resilience of the mats, their ability to recover after each natural disaster, demonstrates their incredible adaptability to harsh conditions. This resilience is crucial for the subsequent stages of land conquest. Without it, any progress into the interior of the continents would be impossible, as the fragile colonies would not withstand the vagaries of the tides and desiccating winds. The Ordovician world was also shaped by global sea level rise. Shallow oceans flooded vast tracts of continents, creating vast tidal flats. These vast expanses offered truly limitless opportunities for the spread of microbial mats. In places where the water remained shallow and calm, mats covered vast areas, uniting separate bodies of water into a single living network. When sea levels fell again, exposing new areas of land, the mats rapidly overwhelmed them. During these great cycles of flooding and retreat, biological mats gradually reclaimed more and more territory from the elements. Under certain conditions, we notice thin green films among the dark microbial mats. These are close relatives of algae. In conquering land, plants didn't just ensure their own survival. They completely reshaped the entire planet to suit their needs. The conquest of Earth by plants is one of the greatest events in the history of our planet. This epic process begins with humble microscopic mats clinging to coastal rocks and continues through the evolution of the first moss-like pioneers. Step by step, they acquire new superpowers, a protective cuticle, respiratory stomata, rhizoids for anchorage, true roots, and finally, vascular tissue for transporting water. This process culminates in mighty forests, capable of altering the very atmosphere and climate. Each evolutionary step built on the previous, transforming plants from fragile and vulnerable creatures into a dominant force on the planet. By the end of the Devonian, Earth was no longer a barren world of bare rocks and thin soil. It had transformed into a planet of forests, fertile lands, flowing rivers, and oxygen-rich air. The greening of the continents was complete, and the echoes of this momentous event will resonate in every subsequent chapter of life's history. Imagine these pioneers. Their bodies are still quite fragile, lacking the internal reinforcement that will one day enable their descendants to soar upward toward the sun. For now, they can only spread out across the surface, clinging to it as long as possible. And yet, within these simple organisms, a fundamental mechanism has already been activated that will determine the future of all life on land. Their photosynthesis pigments greedily capture sunlight through their thin cell walls, triggering the movement of life-giving fluids within. They are capable of slow but steady progress and use microscopic spores to reproduce. Unlike their algae ancestors, to whom they owe their existence, these creatures have taken a decisive step. They no longer need to be constantly submerged in water. They have learned to survive in a much more hostile environment. And this environment was truly merciless. Let's travel to the ancient shore and see what they had to face every day. The mighty ocean retreats, and these tiny colonies are abandoned to their fate. Now they are alone with the scorching rays of the ancient sun, with wild temperature fluctuations and winds that suck out moisture with relentless ferocity. The film of water that gives life evaporates in minutes, and in its place, crystals of caustic salt appear. And above all this is a sky without an ozone layer to shield from deadly ultraviolet radiation, conditions that seem incompatible with life. But these amazing plants, true pioneers of land, have found a way to withstand the elements. Just look at how they accomplish this. They remain tiny and squat, so that as little of their body as possible is exposed to the deadly air. Their tissues have learned to act like sponges, storing just enough water to survive the driest hours. And as soon as moisture returns with rain or morning dew, they instantly absorb it, revive, and restart the process of photosynthesis. This ingenious survival strategy allows them to thrive in cracks in rocks and any depressions where water lingers a little longer than on exposed stones. Thus, step by step, these pioneers conquer the lifeless rocks. Their delicate green carpets, like living paint, brighten the gray and monotonous landscape. To move water and nutrients through their bodies, these tiny plants rely on the simplest physical process, diffusion. They lack complex vessels or canals, so they simply cannot grow tall. However, their groundedness conceals enormous strength. Where microbial mats have already created a thin layer of sediment, these bryophytes find a secure home. They cling to the surface with thin threads called rhizoids. These threads aren't roots as we know them. Rather, they're tiny anchors, delicate protrusions that, like a climber's fingers, dig into the slightest irregularities in the rock to hold the plant in place. Moreover, these rhizoids are capable of absorbing water directly from the moist film surrounding them, providing nourishment where there's no hint of soil. Even reproduction for these creatures is still inextricably linked to water. Fast forward to a time when the air humidity rises. Early land plants release their spores from special capsules that rise above their bodies. When a raindrop lands on one of these capsules, it bursts, sending a cloud of microscopic spores flying in all directions. Each spore is a tiny arc, encased in an incredibly durable shell made of a substance called sporopollenin. This organic material is virtually resistant to decay and desiccation, making it ideal for air travel. Without this protection, dispersal over land would be simply unthinkable. Most spores settle close to the parent plant, but the luckiest are carried by gusts of wind and embark on a long journey to found new colonies far beyond their native rocks. Their life cycle alternates between two distinct stages. The spore grows into the green plant we see on the rocks, the game to fight. Within it, specialized structures mature that produce reproductive cells, gametes. And here, water comes into play again. For fertilization to occur, the male cells, the sperm, must make a desperate swim through a thin film of moisture to reach the female eggs. Once fertilization occurs, a new drama begins. A new generation, the sporophyte, grows from the fertilized cell. It develops the very same capsule containing the spores, which then disperse to begin the cycle anew. This system forever binds them to the aquatic element. However, the key innovation, a true breakthrough, is that these plants spend most of their lives on land, in the air, continuing to photosynthesize. The gradual spread of these organisms begins to change the very appearance of coastal zones. Their green cover darkens the rock surfaces, causing them to absorb more solar heat and thereby slightly altering the local climate. Generation after generation, these plants live and die. Their dead particles, mixing with wind-blown dust, begin to create something entirely new, a thin, barely noticeable layer of organic matter. Over time, this process will lead to the formation of the first primitive soil on the planet. When it rains, the water reacts with this organic matter, accelerating the chemical breakdown of the rock beneath. The minerals slowly disintegrate, releasing nutrients for future generations. This endless cycle of growth, death, and weathering lays the foundation for a future ecological revolution. These colonizers are most successful in the wettest corners. Recesses in the rocks where rainwater collects become veritable miniature gardens. Here, bryophyte plants grow especially densely, forming dense mats that, like sponges, absorb and retain moisture. Such oases of life produce more spores and biomass, further enriching the environment. In secluded crevices, protected from the drying wind, green islands of life survive much longer, demonstrating the importance of microclimate at the dawn of land colonization. However, not every attempt is successful. Billions of spores landing on dry stone simply die. Many green islands dry out completely, leaving behind only faded remains. And yet, their resilience is sufficient to maintain an unbroken chain of generations. And what about the animal world? In that distant era, when life was concentrated in the ocean, these tiny land conquerors had virtually no enemies. Of course, some primitive crustaceans had already made their first forays onto the damp shores, but their impact on plant colonies was negligible. The lack of serious herbivorous predators gave these plants an incredible advantage. Their main enemies were not living creatures, but the very physics and chemistry of this world. This relative safety couldn't last forever, but it gave them invaluable time to establish themselves on land without the constant threat of being eaten. Over time, their expansion transformed coastal landscapes. What had recently been bare rock covered in slippery microbial films now became a patchwork of green cushions. In intertidal zones, these pioneers lined the water's edge, just above the reach of the waves but close enough to receive life-giving moisture. In river floodplains, where the water periodically overflowed, entire carpets of these primitive forms emerged, disappearing only when drought set in. Before us are the very first true terrestrial ecosystems, albeit tiny, and incredibly fragile. The primary evidence of these monumental events comes from fossilized spores sealed in ancient sedimentary rocks. The earliest of these, with their characteristically strong walls, were found in Middle Ordovician rocks. These microscopic fossils, invisible without high magnification, tell us the story of those who were the first to venture out of the ocean. They are irrefutable evidence that land colonization was already well underway at that time, albeit in small, isolated areas. In these tiny traces, we read the prologue to the exciting future of all life on Earth. Yet, despite initial successes, this entire process of land colonization remained a risky experiment. The success of these bryophytes depended on their unique ability to exist on the border between two worlds. They were still slaves to the water when it came to reproduction, but they had learned to live and breathe on dry land. Their tissues, exposed to all winds, were constantly pressurized by the sun's rays, but they acquired the astonishing ability to dry almost to the point of non-existence, then revive again after the first rain. It was this incredible resilience to fluctuations in humidity that distinguished them from their aquatic ancestors. Seizing every opportunity, every drop of dew on the rock surface, they created an entirely new habitat. Each tiny step forward strengthened the planet's organic cover, preparing a springboard for further advances. Their greatness lay not in their size, but in their incredible tenacity. Generation after generation, they established themselves, scattered spores, died, and fertilized the lifeless rock. Their life cycles slowly but surely thickened the organic layer, altering the chemical composition and physical properties of the surface. They transformed the bare rock into something capable of supporting more complex life. And although they themselves remained simple, their activity was truly revolutionary. They became the foundation, the first true land plants, setting the stage for all subsequent acts of evolution. And so, on the damp rock surfaces where these pioneers huddled, a new, ingenious invention emerged that would forever change the balance of power in the struggle for survival. This invention was the cuticle. A thin but incredibly strong layer of waxy substance covered their unprotected tissues. Without it, moisture evaporation was catastrophic. The sun heated the plant's surface, the wind blew away the precious film of water, and the cells quickly died from dehydration. But with the advent of the cuticle, everything changed. This waxy layer was hydrophobic, meaning it repelled water, creating a reliable barrier that prevented moisture from evaporating from within. Even the thinnest cuticle film was crucial, allowing the cells beneath it to retain water much longer than they could do naked. This was a true breakthrough, paving the way for the conquest of even harsher and drier territories. Let's fast forward hundreds of millions of years to a world where life was just beginning to take its first steps from the ocean to land. It was a hostile world for the fragile green tissues of plants, and to survive, they needed a brilliant invention, and it appeared. It was a thin, waxy layer covering their surface, a kind of waterproof cloak that radically changed the rules of the game. This protective film didn't grant plants complete freedom from water, but it loosened the deadly grip of eternal dependence. Now they had time to spare, precious hours and even days between torrential rains. vagaries of the weather, or the receding tide. However, as often happens in evolutionary history, solving one problem immediately creates another. This waxy shell, known as the cuticle, was a double-edged sword. It was excellent at retaining precious moisture, but it also turned the plant into a sealed container. Life, after all, requires constantly inhaling carbon dioxide from the atmosphere and exhaling oxygen for photosynthesis. If the entire surface is hermetically sealed, this vital gas exchange stops, and metabolism slows to a critical point. Most likely, the very first land explorers found a compromise. Their protective covering was so thin that it provided only partial protection without impeding tissue breathing. But evolution did not stand still. As the cuticle became thicker and more robust, plants had to seek new, more sophisticated engineering solutions to balance the two competing objectives, not drying out and not suffocating. However, at the dawn of this era, the cuticle had one primary mission: to survive outdoors as long as possible. This move marked the great exodus from a world where life was only possible on a constantly damp surface. And we find evidence of this great step today, peering into the fossilized pages of Earth's history. Microscopic imprints frozen in ancient rocks serve as irrefutable evidence. On these fossilized plant fragments, paleontologists discern subtle patterns on the surface, ghostly traces where a waxy material once covered individual cells. The preservation of these textures tells us that plants of those distant eras already had developed in complex protective layers. Chemical analysis of these rocks reveals traces of a substance similar to cutin, an incredibly decay-resistant compound that makes up the cuticle. This entire body of evidence points to one undeniable fact. By the time plants began their triumphant march across land, protective armor had become an integral part of their structure. Imagine the world in which this quiet revolution took place. It was a land of extremes. Torrential rains lashed down from the skies, instantly turning everything into a swamp, followed by weeks of brutal drought under the scorching sun. The winds here were not gentle breezes, but merciless torrents that desiccated all living things, stripping moisture from defenseless tissues. And in coastal areas, salty fog added to the scorching heat, sucking water from cells like a vampire due to the difference in pressure. In these hellish conditions, the cuticle was more than just a useful addition. It was the only chance for survival. This protection became especially crucial far from the coast, in the interior of the continents, where plants could rely only on rain, not on regular tides. And those species that were able to develop a sufficiently strong shell began a slow but inexorable advance inland, taking the first steps toward colonizing new unexplored territories. But that's not all. This waxy shield had another equally important function. Its shiny, glossy surface acted as a sunscreen. It reflected some light waves, especially the most aggressive ones. Without this barrier, the sun's invisible but deadly ultraviolet radiation would simply burn the delicate internal tissues of plants. The cuticle absorbed and dissipated some of this harmful radiation, minimizing damage and prolonging the life of each individual organism. This additional advantage became a powerful evolutionary stimulus, cementing this trait into the DNA and passing it on from generation to generation. Nature was a great experimenter back then. The cuticle structure of different pioneer species varied greatly. Some created a thin, uniform film across the entire surface, while others demonstrated a more complex approach, a thick, armored layer on top, where the sun was merciless, and a thinner, more breathable layer underneath, in the shade. This diversity reflects a search for an optimal strategy, an attempt to find the perfect balance between water conservation and gas exchange. In swampy lowlands where moisture was abundant, light protection was sufficient. But in drier, more exposed environments, only those with the densest and most reliable covering survived. This diversity tells us that evolution did not follow a straightforward path. It tried dozens of different options, each perfectly adapted to its own tiny ecological niche on the coastline or in flooded areas. And over the course of millions of years, these countless experiments ultimately led to the creation of the most efficient and sophisticated systems. The emergence of the cuticle had the effect of a bomb exploding on the entire planet's ecosystem. Surfaces that had previously only revived briefly after rain could now retain moisture for weeks. This gave spores a chance to germinate when they landed on such protected tissue rather than drying out immediately. But the most important thing happened when these plants died. Their soft tissues quickly decomposed, but the incredibly strong cuticle, composed of stable chemical compounds, survived much longer. It gradually accumulated, mixed with sand and clay, and formed something the planet had never seen before, the complex chemical composition of the first true soils. This process forever changed the carbon cycle on land, adding a completely new dimension to the young planet's appearance. As a result, the coastal landscape was transformed beyond recognition, whereas previously, after rain, rocks were only temporarily coated with a thin, quickly disappearing green slime. Now dense, resilient green carpets formed on them, capable of surviving long periods of drought. These more resilient communities could withstand the vagaries of the weather, protecting the soil particles beneath from being blown away by the wind and washed away by water. Their appearance opened the door to a whole new world, microorganisms, fungi, and the first land arthropods, which found a stable habitat. This seemingly simple adaptation, a waxy layer, set off a chain reaction of profound ecological changes. The cuticle even changed how plants interacted with rain. Water hitting the hydrophobic, water-repellent surface behaved completely differently. Instead of being instantly absorbed, droplets formed beads and rolled down, preventing tissue from becoming oversaturated with moisture and protecting cells from rupture due to osmotic shock. The water was directed into natural channels and crevices, where it was absorbed slowly and in measured doses. These purely physical processes altered the microclimate around the plants, redistributing moisture so that it provided maximum benefit to the entire plant community. Ultimately, this even altered the nature of water runoff on gentle slopes, further promoting soil formation and stabilizing the landscape. Yet, despite all these incredible advantages, the cuticle was no panacea. It didn't grant complete independence from water. For the most intimate process, reproduction, plants still needed at least a thin film of moisture to allow male gametes to reach females. But by reducing evaporation during the rest of the year, The cuticle ensured that adult plants would survive until that moment. Without this protection, the first land colonists would have simply dried out before they could reproduce. Thanks to their waxy shell, they could wait out droughts, bridging the gap between wet periods necessary for reproduction. This seemingly small difference in the grand scheme of evolution had a decisive, colossal impact. Thus, the development of the cuticle became a turning point in the conquest of land. It was the transition from organisms confined to a narrow, perpetually damp strip at the water's edge to creatures capable of surviving in open, windswept spaces. This did not yet lead to the emergence of mighty forests, but it laid the fundamental foundation for survival in the air. It was the first true adaptation to life out of water, a structural change that forever altered the potential of the plant world. Over time, the presence of a cuticle became the hallmark of all terrestrial flora, a trait passed down and refined from generation to generation. And today, geologists and paleobotanists studying ancient rock layers find this crucial evidence on their surfaces. Fossilized fragments with distinctive cellular patterns confirm that all this really happened. From these tiny fragments, a grand story emerges, a story of how plants began to create armor to protect themselves from the elements, preparing to march deeper into the dead continents. While microbial mats had already stabilized the soil, it was the cuticle that became the material shield that allowed the green advance to continue. In those distant eras, over millions of years, these changes occurred agonizingly slowly, almost imperceptibly. The only signs were the gradual accumulation of organic matter in the rocks and the slight darkening of the stones along ancient shorelines. But hidden within these slow steps lay a decisive turning point in the history of life. The wax barrier allowed plants to perceive the air not as a mortal threat, but as a medium they could negotiate with and master. This subtle yet revolutionary change paved the way for the colonization of the continents. But with the advent of a robust cuticle, plants faced an old problem, now on a new scale. The waxy barrier, which had provided such effective protection against desiccation, now completely blocked the movement of gases. Photosynthesis required carbon dioxide, while respiration released oxygen. To balance these needs without sacrificing precious water, evolution created another marvel of engineering: tiny, adjustable openings on the surface that we call stomata. Each stomata is a microscopic pore surrounded by two specialized guard cells. By changing their shape, these cells could open or close the pore, like a gate in a fortress wall. When conditions were moist and safe, imagine the ancient world, where life took its first tentative steps from the ocean to land. For these primitive plants, every drop of moisture was worth its weight in gold. When water is abundant, their cell walls swell and relax, allowing vital gas exchange to proceed at full speed. But as soon as the sun parches the soil, the situation changes dramatically. As the moisture leaves, the cell walls contract, blocking the flow of gases in a desperate attempt to preserve the remnants of life within. This is where one of nature's greatest inventions comes into play: the stoma. What is it? Essentially, it's a microscopic, ingeniously designed airlock in the surface of leaves, a tiny hole that can open to let in carbon dioxide for photosynthesis and close when the air becomes too dry. It's a survival mechanism that locks precious moisture inside the plant, preventing it from dying of dehydration. This system gave the first land plants an unprecedented level of control over their internal environment. It allowed them to solve a fundamental, seemingly insoluble problem: how to breathe without dying of thirst. We find evidence of this evolutionary breakthrough in the most ancient times. Let's travel back hundreds of millions of years to the dawn of plant life on land. Fossilized remains of the cuticle, the protective film of the first plants, have preserved imprints of these very pores surrounded by specialized guard cells. This is irrefutable proof that plants developed this vital adaptation during the earliest stages of their conquest of land. The very presence of stomata in the oldest fossils tells us that the critical problem of balancing gas exchange and water loss was solved within the first tens of millions of years after life emerged from water. Moreover, the fact that stomata independently emerged in different plant groups only underscores their colossal importance for the entire emerging terrestrial ecosystem. For survival on land, this mechanism, known as the stomata, became key to everything. Its operation is inextricably linked to water balance. In the earliest primitive plants, control of these pores was probably ridiculously simple. Everything depended directly on the amount of water in the tissues. When the water pressure inside the guard cells decreased or increased, their shape changed purely mechanically, causing the pore to either open or close. But evolution did not stand still. In later generations of plants, this system evolved into a highly complex mechanism, controlled by hormonal signals responding to light intensity and even the concentration of carbon dioxide in the atmosphere. However, even in its most primitive, purely mechanical form, this innovation gave plants an incredible advantage. It allowed them to efficiently absorb solar energy without the risk of becoming a dry, lifeless mummy. The impact of the stomata on plant physiology cannot be overstated. By providing this adjustable gate, they enabled photosynthesis to proceed at a rate unimaginable with only a thin cuticle or exposed tissue. They gave plants the ability to fine-tune their internal processes, carbon dioxide levels, water balance, and ultimately find the perfect balance between growth and survival. These are the factors that determine a plant's ability to survive in the harsh conditions of the New World. Thanks to stomatosis, plants learn to adapt to daily and seasonal roller coasters, fluctuations in temperature, humidity, and light. This allowed them to expand far beyond their original habitat. Consider, where previously mosses and their relatives could only exist in dark, damp crevices or at the water's edge, plants with stomatosis were able to expand into open, sunlit spaces. They could now withstand much longer periods of drought, instantly revive after rain, and greedily absorb sunlight. Their efficiency increased dramatically. As a result, we see the planet itself changing. Vegetation is no longer sparse, isolated pockets of green. It now spreads as a continuous carpet, a thick curtain. This green cover is becoming increasingly dense, encompassing coastlines, river floodplains, and even gentle slopes that only yesterday were lifeless deserts between rains. But the ecological significance of stomata extends far beyond individual plants. By increasing their photosynthetic capacity, they began actively extracting carbon dioxide from the atmosphere on an industrial scale. This, in turn, altered the chemical composition of the air at the planet's surface, enriching it with oxygen during daylight hours. Imagine billions upon billions of tiny pores working in unison across the planet. Over millions of years, this collective effort had a profound impact on the composition of the atmosphere. And although global changes occurred slowly, step by step, it was these processes that triggered the long-term decline in carbon dioxide levels that became the hallmark of the Paleozoic era. Each tiny pore contributed to the monumental planetary shift that accompanied the triumphant advance of plants on land. Fossil finds reveal another astonishing detail: how these ancient plants adapted to local conditions. In deposits corresponding to a more humid climate, we see a lower density of stomata on the stems, as the risk of water loss was minimal. However, in drier conditions, their density increased dramatically. This allowed the plants to retain moisture more effectively, and when the rare opportunity arose, for example after rain, they could open up all their numerous pores and greedily absorb carbon dioxide. These differences are striking evidence of evolutionary flexibility. Even then, plants had learned to fine-tune their survival strategies depending on the climate and microenvironment. The very structure of the guard cells provided a purely mechanical advantage. Their shape, often resembling a pair of buds in early plants, allowed them to bend when swollen with water, opening the pore, and contract when the moisture left, reliably closing it. This simple physical system required no complex biochemistry. It operated solely on changes in intracellular pressure. Its genius lay in its reliability. The gate opens when water is abundant and seals tightly when it is scarce. This direct connection to the environment, this automatic feedback mechanism, allowed them to survive in a world of fickle weather and unpredictable precipitation. The presence of stomata also influenced the interaction of plants with the soil and atmosphere. When the pores are open, plants release water vapor. This process, called transpiration, slightly increases the humidity of the air just below the ground surface. This could have created tiny but favorable microclimates that reduced evaporation from the soil and helped other organisms survive. River currents carry silt to shallows, where it becomes firmly anchored in firmer, life-bearing soil. This stabilizes small river deltas and significantly slows their erosion. As erosion slows, new zones suitable for colonization are increasingly formed. This process continues, and its consequences become ever more widespread. The more stable an ecosystem becomes, the more life it can support, and the increase in life in turn contributes to further stabilization. With each new cycle, life's footholds on Earth become ever wider. Over time, microbial mats become true architects of the coastline. They smooth surfaces, enrich sediments with organic matter, and create a unique microclimate. Their stability ensures that each new tide doesn't erase all traces of life. Although these communities lack leaves, stems, or roots, they represent a crucial step in evolution. They demonstrate that life can not only exist at the edge of land, but also gradually shape the conditions for its own flourishing. These slow, almost imperceptible processes lay the foundation for the subsequent emergence of organisms with more complex tissues and structures designed to address the enormous challenges of life far from the sea. The Ordovician coastal world has not yet turned green. Instead, it is covered with films of microbes that form a hard crust and frame shallow pools. On a larger scale, when plants became numerous, their combined activity began to influence the global water cycle, actively transferring moisture from the soil to the atmosphere. Although this effect was still limited in the early Paleozoic, it foreshadowed the enormous role forests would play in regulating the planet's climate in the future. From a procreative perspective, the stomata also played a crucial role. Now, the mother plant could survive long enough to endure drought and await favorable conditions for the completion of the spore production and dispersal cycle. While moisture was still required for fertilization, the plant's own survival between rainfalls became key. The ability to lock water within itself allowed it to survive these dry periods and wait for the right moment to release viable spores. Thus, this adaptation ensured not only daily survival, but also the continuity of generations. In the geological record, we see that the earliest evidence of stomata appears simultaneously with the dramatic increase in complexity of terrestrial ecosystems. Spore clusters, fragments of cuticle with pores, and imprints of primitive plant bodies all appear together, painting a picture of the formation of the first true plant communities with their own unique characteristics. This event marks an entirely new stage in the colonization of land. Plants no longer simply passively adapt to external conditions. They begin to actively control their internal environment. Thanks to stomata, they become more independent of a constant film of water, opening up new horizons for dispersal to the most diverse and unpredictable corners of the planet. The visual impact of these changes must have been striking. Instead of fragile, delicate carpets that withered at the first sign of drought, the landscape was now adorned with a much more resilient and durable green cover. Slopes that had once been completely lifeless between rains now retained their color, thanks to plants learning to manage their resources efficiently. Green patches merged, creating the first semblance of landscapes as we know them. Stable vegetation rather than a temporary green veneer. The ability to open and close pores gave these plants their own rhythm of life. Their activity now reflected natural cycles, more dynamically linking them to the alternation of day and night, wet and dry, calm and storm. Thus, the stomata became the second most important adaptation that strengthened the plant's foothold on land. Following the protective cuticle, it provided a regulated channel between the plant's interior and the external atmosphere. It embodied the perfect balance between conservation and exchange, allowing plants to effectively feed on sunlight without risking death. This balance became essential for the flourishing of life on land, and once established, it forever became a distinctive feature of almost all land plants. The conquest of land took another giant step forward. These tiny pores, scattered across the first leaves and stems, imperceptibly but irreversibly changed the face of the entire planet. The possibilities for life beyond the sea expanded, but having solved the problem of desiccation and gas exchange, plants faced a new threat. To survive, they needed to remain in place, resisting gusts of wind and currents of water, especially on bare rocks or in loose sediments. To achieve this, primitive plants used thread-like outgrowths known as rhizoids. These thin threads sprouted from the plant's body, clinging to the surface and anchoring it in place. Imagine a lifeless, harsh world where bare rocks meet water. Here, in the cracks and tiny depressions, the first conquerors of land waged their desperate struggle for survival. To stay on this inhospitable surface, they need an anchor, and this anchor comes in the form of rhizoids, tiny, thread-like appendages that cling with a death grip to rock and sediment. These aren't roots, as we know them. Rhizoids lack a complex vascular system capable of pumping water and nutrients from the depths. Their job is simpler, but no less important, to anchor themselves. Like climbing hooks, they hold the plant's delicate photosynthetic parts in place, giving them a fighting chance against the elements. Let's fast forward millions of years and see what this means in practice. A relentless downpour begins, or a mighty ocean tide crashes onto the shore. Any unwary creature without a secure foothold would be instantly washed away, carried away by the raging currents, or blown away by a gust of wind. Such a colonization would be doomed from the start. But the rhizoids hold the line. These tiny threads cling to the substrate and don't let go, preserving fragile life. However, they also make a modest contribution to nutrition. Each filament, like a sponge, is enveloped in a thin film of water. And through this film, drop by drop, not only life-giving moisture, but also dissolved mineral salts, precious phosphates and nitrates, seep into the plant. Unlike true roots, which can extract water directly from soil particles, rhizoids operate by diffusion. The process isn't the most efficient, but on constantly moist surfaces, it's sufficient for survival. Thus, thanks to these structures, the plant ceases to be a closed system. It extends its tentacles into the surrounding world, establishing contact with the microscopic environment around each grain of sand. This connection, however weak, significantly expands access to the resources necessary for growth. Nature, as always, is inventive. The structure of rhizoids varies depending on conditions. Some species produce simple, single-layered threads that simply penetrate the soil. Others, living in harsher conditions, form multi-layered, strong fibers with transverse partitions, creating a much more secure anchorage. Where water flows with particular force, it is precisely these thick, multi-layered rhizoids that help retain more moisture. And in areas with a thin layer of soil, graceful single threads are abundant. This diversity is a direct reflection of the variety of environments that ancient life colonized, from tidal flats to riverbanks and perpetually damp rock ledges. In each of these ancient ecosystems, rhizoids were a key adaptation. They gave plants the most important thing: time. Time to grow, reproduce, and spread. Finding a direct imprint of such a fragile organ in fossils is an incredible stroke of luck for a paleontologist. However, like detectives of the past, scientists are finding indirect evidence confirming their existence. Fossilized plant remains from the Silurian period show tiny scars at the attachment points, clear evidence that they had supporting structures. Moreover, the very structure of ancient sedimentary rocks tells a story. We see thin layers of sediment left intact where erosion should have long since washed them away. This pattern points to one thing: an invisible network of plant fibers held the sediment together, making it stronger. Rhizoids acted as a stabilizing agent at the interface between nascent life and dead land. Their influence wasn't limited to a single plant. Imagine entire colonies of mosses growing. Their interconnected rhizoids weave into a single, strong carpet that entangles with soil particles, binding them together. Now, rains and tides can no longer so easily carry the soil to the sea. Sediments that would have previously been lost remain in place, gradually accumulating organic matter from dying plants. Generation after generation, this relentless process triggers the greatest transformation on the planet, the creation of the first true soil. Of course, it's still thin and fragile, just a mixture of organic remains and mineral grains. But it is already an entirely new layer on the Earth's surface, an environment that life itself has created for future life. These tangles of rhizoids become the first megacities of the microcosm. Fungi find refuge here, forming alliances that greatly enhance the exchange of nutrients. Tiny invertebrates, the first land animals, explore these tiny labyrinths, finding shelter and food. Ecosystems, once primitive, begin to become more complex. Thus, rhizoids transform from simple anchors into architects of a new world, scaffolding upon which the increasingly complex edifice of life is erected. Of course, their success depended directly on water. In constantly damp places, they performed their function perfectly. But as soon as the environment became slightly drier, their limitations became apparent. Without vascular tissue, they couldn't transport water over long distances or extract it from deep layers. This forever tied them to shallow soils, damp rocks, and river floodplains. But within these niches, their grip was ironclad. They became a crucial transitional link in evolution, no longer the primitive anchors of algae, but not yet true roots. Rhizoids also played a crucial role in reproduction. To give birth to a new generation, a plant needs to raise its reproductive organs, the sporangia, as high above the ground as possible. But without a reliable anchor, the weight of these structures would simply topple the entire plant. Rhizoids provided the stability that enabled this small but crucial vertical leap. The airborne spores were picked up by the wind and carried over much greater distances, allowing plants to conquer ever new territories. Thus, these humble threads indirectly contributed to the great green conquest of the planet. And now the landscape begins to change. The bare, lifeless rocks along streams and where water seeps are covered with dark green velvet cushions. On the rocky slopes, they form a living carpet, tightly clinging to the surface. From a distance, they look like mere patches of color, but upon closer inspection, we see a complex network of fibers intertwining every grain of sand, every crack. The shoreline is transformed. Where once there was only a temporary slippery film of algae, now resilient plant communities form, firmly anchored to the land. But that's not all. The rhizoids also waged chemical warfare. Penetrating microcracks in the rocks, they secreted weak organic acids. Drop by drop, year after year, these acids slowly but surely broke down the rock. They dissolved minerals, releasing the nutrient ions trapped within. Some of these substances were absorbed by the plants themselves, while others accumulated in the forming soil. This process increasingly linked life and non-living matter, altering the very chemical composition of the planet's surface. Thus, a powerful feedback loop was triggered. The rhizoids broke down the rock, enriching the soil, and the richer soil allowed new, even more numerous colonies to grow. Despite their importance, the capabilities of rhizoids were limited. They couldn't penetrate deep into the soil and weren't capable of supporting large, massive plants. Their role was limited to holding and superficial absorption. But within these modest capabilities, their role was absolutely fundamental. It was that very persistence, the foundation upon which all subsequent complexity grew. Without the ability to anchor themselves in one place, plants would have been washed away long before they could develop more sophisticated organs. It was in this struggle for survival that one of the most important alliances in the history of life was born. Numerous fossilized spores of ancient plants bear the imprint of fungal structures, indicating an ancient symbiotic partnership. The fungi, with their fine threads, extended far beyond the rhizoids, penetrating the soil and extracting phosphorus and other minerals inaccessible to the plant. In return, the plant, a master of photosynthesis, generously shared sugars with the fungus. This alliance greatly increased the efficiency of the rhizoids, turning them into entry points for extensive fungal networks. In the grand saga of the conquest of land, rhizoids represent the perfect balance between fragility and unyielding endurance. These simple threads appeared delicate, yet they protected the first plants from forces that would have destroyed them. They allowed them to remain in place long enough to grow, reproduce, and when they died, leave behind organic matter that would become the soil for future generations. With their tenacity, they transformed bare, damp rocks into the first fragile yet living earth. But beneath the surface, unseen by all, a new, even more powerful community was forming. Fungal threads known as hyphae were tightly intertwined with the rhizoids, extending deep into the surrounding soil. This relationship is the earliest evidence of what scientists would later call mycorrhiza. In this alliance, the plant supplied energy in the form of carbohydrates, and the fungus acted as a tireless supplier, bringing water and minerals from a much larger area than the rhizoids alone could cover. It was an ancient partnership, the beginning of a great friendship, traces of which we find in fossilized spores hundreds of millions of years old. In fossils from that ancient era, paleontologists find astonishing imprints of fungal threads. This is irrefutable proof that the great alliance between the plants and fungi began at the very dawn of life on land, becoming the key to the conquest of the continents. Imagine the ingenious simplicity of this partnership. The finest fungal threads, like microscopic drills, were able to penetrate where no root could reach, the tiniest cracks in rocks and dense soil. They became the hands and mouths of plants, bringing vital resources from the deepest depths. These underground allies were truly engaged in treasure hunting: phosphorus, nitrogen, rare trace elements, everything essential for growth, but found in a form virtually insoluble in water. Without the help of fungi, these priceless nutrients would have remained forever locked away in minerals, inaccessible to the first explorers of dry land. By channeling this vital elixir directly to their green partners, the fungi literally terraformed the planet, greatly increasing the chances of success for these first timid plants. In exchange, the plants shared precious rewards with the fungi: sweet sugars, solar energy, transformed through photosynthesis. In that ancient world, where organic matter was extremely scarce, this was an invaluable resource. Each partner received what they could not obtain on their own. Together, they became a force capable of accomplishments unimaginable for either alone. And this union immediately began to change the face of the planet. At first glance, this world may appear completely empty, but in fact, fundamental, albeit almost imperceptible, changes are taking place within it. Gradually, layer by layer, living mats expand their influence, preparing the land for the triumphant emergence of plants. Their role seems modest, but without their stabilizing grip, without the gradual transformation of soil and rock, the path forward for life would simply be impossible. And so, on the damp surfaces of rocks and shorelines, beyond the microbial thickets, the first colonizers, similar to bryophytes, begin to appear. These organisms do not yet strive upward. They bear no resemblance to the giants of the forests of the future. They are small, soft-bodied patches of greenery that most closely resemble the mosses and liverworts of the modern world. They grow tightly pressed to the ground, clinging to rocks and mud where life-saving moisture lingers longest. Imagine one of the greatest dramas in the history of the conquest of our planet unfolding. Here, on ancient land, a quiet but momentous revolution is taking place. The key to this revolution is xylem, a brilliant invention of nature that forever changes the rules of the game for the plant world. This tissue solves a fundamental problem: how to lift water upward, defying gravity itself. It is xylem that allows plants to reach for the sky, to become taller and more powerful than ever before. Where previously only thin, barely noticeable films of life had spread across the rocks, now, thanks to the fungal boost, dense, voluminous carpets of plant communities began to form. Receiving abundant nutrition, the plants became more resilient, more vigorous, and expanded into ever-new territories. This nutrient-rich cocktail from the fungi acted as a growth stimulant. Photosynthesis increased at double the rate, leading to rapid growth. The green mats grew thicker, clinging to the soil more effectively and, most importantly, retaining precious moisture longer. Oases of stability were created, which in turn facilitated the emergence of new colonies nearby. The greening of shorelines accelerated dramatically, while the threat of devastating floods was reduced. Thus, the invisible presence of the fungi greatly enhanced the impact of the plants on the surrounding world, but their influence also extended to the planet's chemistry itself. Fungi are veritable chemical factories. They secreted special organic acids that slowly but surely eroded rock, accelerating the weathering process thousands of times. This chemical assault released calcium, magnesium, and potassium ions from their mineral prisons, which immediately entered the soil solution. Some of these elements were immediately absorbed by plants, while others accumulated, enriching the soil and preparing the ground for future, more complex life forms. A vast mechanism was set in motion, which paleontologists call a positive feedback loop. It was the perpetual motion machine of life itself. The more fungi, the more actively the rocks are eroded. The more actively the rocks are eroded, the more nutrients are in the soil. The richer the soil, the better the plants grow. And the more plants, the more food for the fungi. which grow even more. And so, loop after loop, million years after million years, this cycle transformed dead, lifeless rock into fertile soil capable of supporting entire ecosystems. And we know this isn't just a beautiful theory. The stone preserves the memory of this alliance. The oldest plant spores, so-called cryptospores, and other plant remains bear traces of fungal invasion. Under a microscope, microscopic fungal structures can be seen penetrating fossilized plant tissue. These scars of symbiosis are the best proof that the bond between fungi and plants was no accident. It was ingrained into the very fabric of their physiology. Even genetic studies of modern species confirm that their common ancestor, the one that formed this alliance, is hundreds of millions of years old. This great collaboration of microscopic organisms became the foundation upon which the conquest of land was built. And the fact that this partnership has survived to this day in almost all plants speaks to its incredible, resounding success. In terms of survival, fungi became a veritable insurance policy for ancient ecosystems. Imagine a severe drought when the sun scorched all life. At this point, the underground fungal network transformed into a life-saving reservoir. Its microscopic pores retained the last drops of water, gradually releasing them to their green partners. If the soil was poor, the fungal network spread across vast territories, collecting nutrients bit by bit and redistributing them among all members of the community. Essentially, fungi created the first social network in history where resources could be transferred from one organism to another. Even in the ancient Paleozoic, such invisible connections made plant communities incredibly resilient, protecting them from complete destruction during cataclysms. And the manifestation of this hidden power could be seen with the naked eye. Where once shorelines were covered only by slippery films of algae, thick, resilient mats now lay, successfully resisting erosion. And beneath them lurked a secret army, an invisible web of fungal threads that knitted soil particles into a single, strong structure. This network both stabilized the soil and nourished it. And now the planet's surface itself takes on a new texture, a new substance. It was a living, breathing crust, holding the world together from above and from within. These coverings, like a sponge, retained moisture after rains, slowed drying, and created ideal microscopic shelters for the first invertebrates timidly crawling out of the sea. Thus, fungi influenced not only plants, but also the formation of the Earth's entire biosphere. This alliance also altered the great carbon cycle. Plants, taking in carbon from the atmosphere, converted it into sugars. They donated some of these sugars to fungi, which, in turn, respired and returned carbon dioxide to the air. This exchange accelerated the movement of carbon in nature, forcing it to circulate between living organisms and the atmosphere. And as the green canopy spread across the planet, these seemingly insignificant processes led to global changes in the composition of the atmosphere, preparing the world for the giant forests of the future. The emergence of fungal communities was a crucial step in evolution. Plants were no longer solitary fighters, relying only on themselves. They now became part of a complex, mutually beneficial system that united different kingdoms of life into a single superorganism. This cooperation allowed them to conquer territories that were previously completely unsuitable for life. bare rocks, poor sandy soils, and the banks of shallow streams. All these landscapes became habitable as soon as the fungi expanded their living space for their partners, and the plants, in turn, served as an inexhaustible source of energy for the fungi, a luxury in a world where photosynthesis had previously been represented only by ocean algae. The success of one now depended directly on the success of the other, their destinies forever intertwined in a single history. And the planet's physical appearance began to change, reflecting the presence of this union. More and more organic matter accumulated on the riverbanks, causing the soil to become darker and more fertile. Floodplains, which had previously turned into desert after every flood, now remained green longer, and vegetation reliably protected them from erosion. Even at higher elevations from which water had previously flowed instantly, thin layers of moisture were now retained in the soil, held by an invisible fungal network. These changes even affected the ocean. Less turbidity entered coastal waters, and their chemical composition changed. As plants and fungi colonized land, the boundary between sea and continent became increasingly sharp and defined. And these first terrestrial ecosystems were remarkably resilient. Their secret lay in their redundancy. If one plant community perished, spores and mycelial fragments from neighboring areas quickly helped it regenerate. Even if a natural disaster destroyed the entire above-ground part, the fungal network continued to thrive underground, ready to give rise to new life as soon as conditions became favorable. This ensured continuity in a constantly changing climate. The geological record shows us that individual species might come and go, but the great partnership of plants and fungi continued to live, evolve, and slowly but surely conquer the continents. From the vantage point of geological time, we understand that this alliance was a true point of no return, one of the greatest turning points in Earth's history. These were no longer mere clusters of microorganisms. They were complex, integrated systems in which physics, chemistry, and biology worked together to create a more stable, fertile, and diverse world. The conquest of land proceeded so rapidly precisely because plants weren't alone. They had silent, invisible allies whose work took place underground, but whose role was absolutely irreplaceable. By the end of this era, the Earth's landscapes were no longer desert expanses with scattered pockets of life. They had transformed into a seamless network woven from plants and fungi, a network that held the soil together, retained moisture, and recycled nutrients. The green cover became denser, the soils deeper, and the atmosphere subtly changed. This alliance, born of chance, created the solid foundation upon which all future terrestrial ecosystems would grow. And now we see plants and fungi continuing their triumphant march, expanding their domain along humid coastlines and flooded river valleys. Imagine how their combined influence begins to literally reshape the very geological fabric of the planet beneath their feet. Rocks that for centuries had succumbed only to the erosion of wind and water are now confronted by an entirely new force, the chemical attack of living organisms. The acids secreted by tiny roots and fungal fibers, along with the organic remains of rotting plants, begin to mercilessly corrode the stone. These combined efforts accelerate the breakdown of solid minerals many times over, transforming indestructible rock into pliable, crumbly particles. During this titanic yet unnoticeable process, the first, still very thin layers of soil are formed on the planet's surface. They are strikingly different from the bare rock or shifting sand deposits that existed here before. This new substance is a remarkable cocktail of mineral grains, organic matter, and billions of microorganisms. And although it may seem fragile, it already possesses incredible stability. This soil is capable of retaining water much longer than bare rock, and it retains heat, creating a much more comfortable environment for life. This, in turn, provides a powerful impetus for the further growth and prosperity of plants. The landscape, which until recently was a completely lifeless desert, is beginning to fill with greenery and life before our very eyes. The role of organic matter in this global process cannot be overstated. As generations of primitive plants like Cooksonia are born and die, their remains accumulate on the surface. And unlike simple microbial films which disappear almost without a trace, plant tissue is a much more durable material. Durable compounds, such as the waxes that coat their outer shells or the sporopollenin that composes their spores, are extremely resistant to decay. They remain in the soil, adding durable fragments that slow overall decomposition. Over time, these remains mix with mineral particles released from the rock by chemicals and weather. This creates a unique matrix, rich in both carbon and nutrients. Each new generation of plants literally grows on the bones of the previous one, gradually increasing the thickness of the fertile layer. This slow, centuries-long accumulation lays the foundation for a much more complex and extensive vegetation in the distant future. Powerful weathering processes are also occurring simultaneously. The very nature of plants changes as they colonize land. They don't yet have true roots, but they already have rhizoids, their primitive precursors, invisible mycelial threads penetrating microcracks, secrete acids that literally dissolve minerals such as feldspar. This process releases calcium, potassium, and magnesium ions, essential nutrients. These become available to plants, stimulating their growth and reproduction. At the same time, the disintegration of rock makes it more porous, allowing water to percolate deeper. This combination of chemical and physical processes initiates great cycles of soil formation that will continue for millions of years. In just a few hundred years, the spread of these primitive soils radically alters the appearance of the continents. First and foremost, the planet's hydrology changes. Where once rainwater instantly flowed in turbulent torrents from bare rocks into rivers and oceans, the soil now acts as a giant sponge, retaining moisture for long periods. Vegetation, nourished by this stored water, is able to survive dry periods. Water percolating through the soil carries dissolved minerals which settle in the lower layers. This begins the gradual division of the soil into horizons, even if this process is still completely imperceptible on the surface. In the earliest stages, these processes were barely noticeable, but over time, century after century, they gained momentum, forming increasingly complex soil profiles. Although these profiles were still shallow and easily eroded during the Ordovician and Silurian periods, their very emergence marked a revolutionary step toward the stabilization of terrestrial ecosystems. The accumulation of organic matter, in turn, fueled an explosion of microbial activity. Billions of bacteria and fungi literally thrived in this new environment, greedily devouring plant debris and recycling nutrients. Their metabolism altered the surrounding chemistry, creating localized zones where unique chemical reactions occurred. These microbial communities further accelerated the conversion of rock into soil, while simultaneously creating ideal microhabitats for other organisms. It was likely at this time that the first the arthropods, began timidly exploring the land, finding food and shelter in these nascent soils. Thus, the colonization of land by plants was directly linked to the emergence and diversity of terrestrial animal life. We find evidence of this ancient process today. Fossilized ancient soils known as paleosols are preserved in sedimentary rocks as successive layers, like pages in a stone book of history. In these layers, paleontologists find traces of primitive roots, organic rich horizons, and clear signs of chemical weathering. All this provides irrefutable evidence of how plants formed the soil. The dating of these finds, dating back to the Middle Ordovician and Silurian, confirms that the process of soil formation was already well underway in that distant era. These data demonstrate that as plants spread, they didn't simply populate the land, they actively reshaped it, creating entirely new conditions for themselves and for those who would come after them. The impact of soils on erosion was colossal. In river floodplains, where water had previously carried away tons of sediment, the soil, held together by plant roots, now held the particles in place with a death grip. This dramatically reduced the amount of sediment entering the rivers. It serves not only as a water supply, but also as an internal skeleton, impregnated with a highly durable substance called lignin. This gives the stems rigidity, allowing them to withstand winds and grow vertically. From this moment on, everything changes. Carbon cycles in soils, entire ecosystems. Plants transform from humble, fragile colonizers into true architects of the Earth's landscapes. The conquest of continents gains incredible momentum, driven by this invisible force of vascular tissues that, like arteries, permeate stems and roots, linking earth and sky into a single, breathing organism. With the advent of xylem, that internal pump that pushes water and minerals upward and gives stems their steel-like rigidity, the evolutionary arms race is just beginning. But for complete triumph, another equally crucial system is missing. And so, in response to increasing structural complexity, nature creates a second vascular tissue that closes the internal cycle of life. This tissue, known as phloem, is a living network of elongated cells. Its mission is to transport precious sugars and other organic compounds created during photosynthesis. And herein lies the key difference from xylem. Whereas xylem was a one-way street from roots to leaves, phloem becomes a complex logistics network with multiple roots. It distributes energy precisely where it is needed at a given moment. Streams and rivers, receiving less silt and sand, changed their dynamics. Their channels became more stable and predictable, and deltas at their mouths formed entirely differently from more solid sediments. Vegetation along shorelines, firmly rooted in the soil, could withstand the onslaught of waves much more effectively than loose sand. It created living protective barriers that reshaped the contours of continents, altering the boundary between land and sea. These geomorphic shifts, in turn, affected marine ecosystems, influencing the supply of nutrients and the distribution of sediments on the continental shelf. The emergence of soil also triggered a powerful climate feedback loop. By storing organic carbon, soil became a vast reservoir that began to influence the composition of the atmosphere. Initially, these reservoirs were small, but as vegetation conquered new territories, they grew and expanded. The carbon dioxide absorbed by plants through photosynthesis was no longer immediately released into the atmosphere, but was instead stored for long periods in organic matter. This, coupled with the formation of carbonates in the soil, gradually reduced greenhouse gas levels. Over millions of years, this process contributed to the global cooling trends that characterized certain periods of the Paleozoic era. Thus, the slow and subtle accumulation of soil had a profound impact on the climate of the entire planet. The physical properties of these early soils varied greatly depending on where they formed. In coastal areas, the soils were saline and often eroded by tides, but even here, vegetation helped stabilize them. In river floodplains, the soils were deeper and more fertile, periodically enriched by fresh river silt. And in highland areas, the soils had a patchy, mottled structure, forming only in cracks and depressions where precious water could accumulate. But in all these environments, the appearance of soil marked a crucial transition from temporary colonization to the creation of a stable, long-lived ecosystem. Plants no longer clung to life on bare rocks. They built and modified their own homes, ensuring a stable future. These soils were teeming with biological activity, involving not only plants and fungi, but also a host of other organisms. The first land animals, such as the centipede-like arthropods, were among the pioneers who began to explore this new world. They fed on decaying plant matter and dug the first burrows, mixing the organic and mineral layers, which promoted soil aeration and accelerated decomposition. This activity, combined with the work of fungi, accelerated nutrient cycling, supporting continuous plant growth. As a result, the soil became increasingly structured, developing channels, pores, and aggregates, further improving water retention and facilitating root penetration. The interaction of plants, fungi, microbes, and animals created a complex system that irreversibly changed the face of the earth. Landscapes with these early soils were strikingly different from the barren, rocky deserts of the past. Green patches of vegetation became increasingly continuous, supported by a stable environment beneath. The soil became loose, pliable, and more resilient to external influences. During a rainfall, it absorbed water, which sustained plant life long after the surrounding rocks had completely dried out. This resilience, developed over generations, contributed to the integrity of the plant cover, which in turn further accelerated soil formation. This initiated a self-sustaining feedback mechanism. More soil means more plants, and more plants means faster and better soil formation. From a geological perspective, the emergence and development of soil represents one of the most significant upheavals in Earth's history. Before plants arrived on land, weathering was dominated by purely physical and chemical processes, slowly affecting rocks. With the emergence of life, weathering became biologically mediated, more rapid, complex, and diverse. This shift had a cascading impact on sediment composition, global nutrient cycling, and many other planetary processes. The chemical composition of the atmosphere began to reflect the powerful influence of life, which we can trace throughout geological history. We are witnessing the birth of the first true roots. Unlike their predecessors, the rhizoids, these new organs contain vascular fibers, true water transport arteries. Plant roots are a key tool that allowed them to conquer land. They penetrate deep into the soil, branching as they grow, which not only makes the plant incredibly resilient, but also opens access to resources hidden from surface dwellers. This crucial evolutionary innovation gave plants freedom. They were able to leave their tiny, perpetually wet areas and adapt to a wide range of conditions, colonizing deep floodplains and even arid uplands. Paleontologists find the oldest evidence of roots in Silurian and early Devonian deposits. Fossils from those times reveal small cylindrical structures that radiate deep into the sedimentary rocks like rays. These stone records preserve traces of vascular tissue, irrefutably proving that these were not simply supporting threads but fully fledged organs with a developed internal transport system. In some cases, scientists discover that both the roots themselves and the surrounding sediments bear traces of chemical changes. The roots and associated fungi literally dissolved minerals, actively participating in the formation of the soil layer. These traces are proof that the roots served a dual role. They not only held the plant in place, but also actively sculpted the earth itself, drawing nutrients upward and enriching the soil with organic matter. It is this dual function, mechanical and chemical, that fundamentally distinguishes them from all previous fastening systems. Thanks to roots, plants gained access to a stable and much more reliable source of water. They no longer had to rely solely on rain or surface moisture. They could draw water from reservoirs hidden deep underground. This greatly increased their resilience to periods of drought and allowed them to survive in the unpredictable climate of the ancient world. The deeper and more extensive the root system, the more reliable the protection from drought. But even shallow roots provided a huge advantage over rhizoids, firmly anchoring plants in the soil, so they could withstand fierce winds and torrential rains. Having acquired this remarkable resilience, plants began a victorious march across the planet, occupying territories previously considered completely lifeless. The roots' branching structure allowed them to explore vast volumes of soil. Each root branch diverged and repeatedly divided into ever smaller structures. At the tips of these branches were root hairs, which increased their surface area hundreds of times, ensuring maximum contact with soil particles and the water film. This architecture allowed for the absorption of water and dissolved minerals with incredible efficiency. By partnering with fungi, the roots utilize these resources in a way never before possible, supporting growth and reproduction on a scale unimaginable for plants without such a system. The result was larger, stronger plants, capable of reaching for the sky and capturing more precious sunlight. But beyond the life of an individual plant, roots played an even more important, truly planetary role. When root systems penetrate the soil, they bind its particles together like rebar, dramatically increasing soil cohesion and reducing erosion. This, in turn, stabilizes riverbanks and floodplains, as significantly less sediment is washed into waterways. River channels become more permanent, and floods on flat plains last longer. At higher elevations, roots act like a sponge, slowing rainwater runoff and increasing its absorption into the ground, significantly reducing the intensity of floods downstream. These landscape changes impart a whole new level of stability to the planet's surface. Roots also greatly enhance chemical weathering by penetrating tiny cracks in the rocks. By widening these cracks and releasing acids, they literally dissolve solid minerals. This process releases ions that not only nourish the plant itself, but also enrich the soil for future generations. Thus begins an endless cycle of life. Plants help preserve and improve their own environment. The absorption of minerals and the accumulation of organic matter in the soil create a cycle that saturates it with nutrients and carbon. Over time, these fertile soils become the cradle of more complex plant communities and the foundation for supporting large ecosystems. The role of roots in soil formation steadily increased, continuing the titanic work begun by rhizoids and fungi. The fossil record provides irrefutable evidence of this process. In ancient soils of the early Devonian, we see traces of roots, known as rhizoliths, penetrating layers of sedimentary rock. These fossilized channels are evidence that plants actively invaded the soil, changing its structure from within. Near these rhizoliths, paleontologists find deposits of organic carbon, proving that roots made a colossal contribution to the development of soil cover. By this time, plants were no longer simply passive inhabitants of the surface. They had become active engineers of the underground world. Deep roots not only change the scale of plant growth, but also provide them with a more abundant and constant water supply. This enables them to develop larger, above-ground organs. When the underground system can fully meet the plant's water and nutrient needs, tall stems and complex branching systems become possible. This transition paves the way for the emergence of vascular plants with true leaves and woody tissues, although their full development will take millions of years. The emergence of roots marks the beginning of a new era in plant architecture. During this period, the ancient alliance between roots and fungi deepened. This micro-level partnership allows fungi to literally integrate into the root system. Fungal hyphae penetrate root cells and form specialized structures for resource exchange. These associations dramatically increase phosphorus absorption, which was especially critical in the nutrient-poor soils of ancient land. This mutual benefit ensured the prosperity of both partners. In modern ecosystems, the vast majority of plants retain this mutually beneficial partnership, indicating its incredible antiquity and enduring importance. The fact that these relationships have been preserved in almost all plant groups underscores their fundamental role in the conquest of land. Roots also have a profound impact on the global water cycle. By absorbing water from the soil and releasing it as vapor through the stomata on their leaves, plants enhance evaporation. This movement of water from the ground to the sky directly influences humidity and local climate. Although vegetation was not as abundant in the Silurian and early Devonian as it would be in subsequent eras, the cumulative impact of rooted plants had already begun to alter the distribution of moisture and precipitation on a scale noticeable over geological time. These changes led to large-scale atmospheric and climatic shifts, directly linking the evolution of roots to planetary processes. The emergence of roots also brings about fundamental changes in ecological interactions. Arthropods colonizing land find new shelters and food sources in root-stabilized soils. Invertebrates burrow, creating channels that aerate the soil and facilitate water infiltration, which in turn benefits plants. Detritivores, feeding on decaying root fragments, return nutrients to the system. These interactions weave plants, fungi, and animals into cohesive, integrated ecosystems. Each group influences the others, and together they transform lifeless spaces into dynamic and interconnected communities. In this new era of living landscapes, with the emergence of established plants, landscapes become more cohesive and resilient. Vegetation is no longer limited to fragile mats in damp lowlands. It spreads over vast areas, steadfastly enduring the vagaries of the environment. Green canopies become denser, protecting the land from wind and regulating water flow. Riverbanks become stronger, floodplains more vegetated, and uplands less barren. If we could look down on the continents from above, we would notice them beginning to acquire a permanent green hue. Subtle at first, but already unmistakable. Roots mark the beginning of a long chain of evolutionary events that will ultimately lead to the emergence of majestic forests on Earth.